Thank you. Okay, so we can move to the next session, which would be on connected and autonomous vehicles. So please stay in the room if you are for those presentations. The first one would be the connected autonomous vehicle trial in Queensland, Australia, and we feel privileged to have Amit Trivedi and Professor Sebastian Glaser. So Amit is the Assurance and Innovation Lead at the Queensland Department of Transport and Marine Roads in Australia. Amit and Sebastian, they're leading CAF trial in Mount Isa, and I think they just got back last week or so. So with some more insight into that CAF trial. So Amit, yes, we have your video. Do you want to, so I can stop actually sharing, and Amit, will you go first?
Yes, can you hear me?
Awesome. Yes, yes. So
okay, no, I'm not used to with the Zoom platform. I'm used to with the Teams platform.
So there's a share screen, like a green one in the bottom of the
Yep.
So you can click and then just choose the monitor. Usually people have so many monitors these days. And then again, click on share.
Okay.
So meanwhile, when you are figuring out, let me just give a brief bio. I also I had the pleasure to be guided by Amit during in my former organization, National Transport Research Organization, NTRO, which actually used to be Australian Road Research Board. And so Amit has over 25 years of experience directing and managing innovative and progressive risk assurance and safety management systems, particularly the connected autonomous vehicles, diverse experience within the rail industry and oil and gas sector as well, with dual qualifications in engineering. And also he is a member of Institute of Engineers Australia and both local and international experience. So a true industry leader with published reports and documents from the Queensland government. Okay, so yes, we have your slide, Amit. So I'll mute myself and over to you. Thank you.
Thanks very much. I hope we've got a few videos to share, and I hope the sound from the video also comes through. I think I can see. Okay, so we got only half an hour, and we got quite a lot to cover because there are lots of work packages under the pilot. So I'm going to be quite quick. I'm going to be speaking about our pilot in a pretty high level because I work from the Department of Transport, and our pilot is predominantly looking at the safety impacts and benefits of automated vehicles in Queensland. I'll try to finish my presentation in 10 minutes, and then we'll hand over to Professor Sebastian Glaser, who will walk you through some other work packages that we work on. So there you go. Let's go back to history. The way the automobiles came into the world was 1885. Carl Benz introduced this vehicle, three-wheeled, first patented production vehicle. Others did as well, but it never went to production. And this is how the automobiles came into the world in 1885. And ever since then, we have pretty good evolution of the technology, and Carl Benz company today is Mercedes-Benz. And this is what you see in Mercedes-Benz. So there is a massive development over the years of about 135 odd years. What we know that, yes, there has been quite a lot of development, but there has been one unreliable component present right from the beginning of the 1885 motor wagon, and that is the human driver. So all our projects are about trying to support human driver or potentially replace if we can. Now, while automobiles have evolved significantly, the computer technology has evolved many folds, massively. What you see on the left is a 1885 calculator. Thomas arithmeter, mechanical calculator, and on the right you see is NVIDIA's Orin chip, which packs in, I think, 17 billion transistors and 200 tops of performance. And I think they got a new one now, which is about 4 times as more powerful than this one. So our project is trying to investigate, and as again, our focus is safety impacts and benefits. And we're looking into physical infrastructure, digital infrastructure, road users, how vehicle would interact with others, players on the road, and inside the vehicle, interaction with the human driver by the driving task handover and takeover. While we're doing that, we also did various demonstrations to bring public awareness and growing governments and stakeholders' knowledge. To deliver the pilot, we developed 2 platforms. Both of them are Renault Zoe electric cars. What you see on the top, we call Zoe 1, and on the bottom, very similar looking car called Zoe 2. Zoe 1 had all the state-of-the-art sensors and computers, but was never designed to be an automated vehicle. And what you see in the bottom, that's a Zoe 2. It's a level 4 automated research prototype. In other words, we can set it up to behave like either a level 1, level 2, level 3, or level 4 vehicle in certain conditions. So these are the 2 prototypes we developed. And I'm going to focus onto the physical road infrastructure side of the work package, and Professor Glaser will focus onto remaining work packages. So I'm going to straight show a quick video. This video doesn't have any sound bites with it, but this is Zoe 1 when we put together, and these are the QUT engineers putting Zoe 1 together. Our final report is a public report. It is available on the IMO website. What we did with this vehicle, we went out on a 1,200 kilometer drive around Southeast Queensland, various roads, various weather conditions, day and night, and collected data, worked out the traffic light, traffic signs, and road lines, as well as accurate positioning and what are the impacts or what is actually required. What we came out of that, our results was the report provided quite an interesting insight, and that is, this report was actually published in 2019, so it might not be that interesting today because we know the things have evolved quite well, but at that time it was quite an interesting to know, and that is that the technology is evolving. There are 2 philosophies emerging, and one philosophy is that if human can drive with stereo vision and without any high definition maps in our brains, then automated vehicles should do the same. That's one philosophy. And other philosophy is if you want a high reliability, you will need multiple sensors such as LiDARs, radars, and cameras, as well as some sort of a high definition map or prior maps to achieve high level of reliability. So these 2 philosophies were emerging. One, which is the one which believed that humans can drive without LiDARs or high definition maps, that's Tesla philosophy, and literally everyone else were on the other side. So our conclusion was that if Tesla wins out, we will need to do plenty of work as far as the lines, signs, traffic lights, and all sorts of infrastructure. And if everyone else wins out, there will be almost nothing to be done. Very little that government will have to do as far as physical infrastructure is concerned. But the key component to all that is prior maps, or sometimes called high definition maps. So what we found is multiple sensors, and that is a LiDAR, radar, camera, fusion of them, as well as some sort of prior maps, call it high definition maps. They will be critical. And if that is given, then we will not need to change our standards human standards for line signs, traffic lights would be perfectly fine. And then I will hand over to Professor Sebastian Glaser to talk to you about other work packages.
Thank you very much, Amit. You were almost right, and as I still have the background with Montaisa, where we were, as you mentioned a few weeks ago, to deliver a demonstration of the automated vehicle. So I will continue. Can I have next slide, Amit, please? Yes.
This slide has a sound in it. I hope it comes through.
Yes, this is a presentation of Zoe. Doesn't look that the sound is going through.
So Sebastian, perhaps the sound doesn't come through. Maybe when if you click on that voice thing, the mute sign, I think you can select microphone. You can select same as system.
Okay, correct. Yes, let's see if it works. Is it working?
No. For that mute, there's a kind of like a mute and sound icon. If you select a microphone, same as system, I think it should.
Same as system. Oh yeah, okay. There it is.
Yeah, now let's see.
Any better? No.
Not yet. How about selecting a speaker, same as system as well?
Real text speakers. So let's see if that works.
Well, to be honest, also Zoom is not what.
Any good? Nope.
Yeah, I don't hear the sound. No, not yet. Anyone knows what could be?
No.
When you share screen, you have to check share sound. Kentaro, I think it's Teams when you share the screen. Oh, hang on. No, it's in Teams when you share the screen, then you have to check share sound, but Zoom is different. Yeah, yesterday.
I was hosting earlier today for the Western track, and I had to play the videos for people who could not present in real time. And when I did that, I clicked share sound when I shared the screen in the video.
Oh, yes. So Amit, perhaps you can unshare and then share again.
Okay, let's do that.
When you are sharing screen, then perhaps there's something that you can tick.
Otherwise, I can do it, Amit.
Okay, so what should I do? Oh, here you go, sound share. Here you go. I found it now. Hopefully worked. Sorry about that.
Good.
I learned something as well today.
Can you see my screen now?
Yes.
As our population grows and roads get busier, the Queensland government is committed to supporting transport solutions of the future. That's why we've teamed up with partners like QUT to prepare for our evolution into driverless technology. A purpose-built research vehicle that integrates automated and connected technology into a Renault Zoe electric car. There's a lot of talk these days about driverless vehicles, but the truth is there are no commercially available fully automated cars on the roads today. Some cars have limited automated features like adaptive cruise control. However, no fully automated vehicles have been deemed safe enough to handle Australian conditions. And that's why we're running trials just like this, to ensure every step has been taken for maximum safety in the future. There are several different levels to automation in vehicles. Levels 0 to 1 are older cars that are both hands-on and eyes-on with little to no automation. Drivers need to complete all tasks manually or do a majority of the work. Level 2 is the current level of automation in cars available on the market today. Think Tesla and vehicles with driver assist technology. They are eyes-on and can be temporarily hands-off. They have partial automation, where the vehicle assists the driver with steering, acceleration, or parking. But the driver is still responsible for safety-critical functions and must be ready to take control. At level 3, the biggest leap in automation happens. Here, cars are still eyes-on and temporarily hands-off, but have conditional automation, such as traffic jam assist. This means the vehicle monitors its environment to drive itself in certain conditions. The driver's attention is still required. However, the system will provide a few seconds of warning before handing control back to the driver. Levels 4 to 5 are the highest levels of automation in vehicles. These vehicles are eyes off and hands off. So the driver doesn't need to take control of the car unless they want to. Or at level 5, the vehicle can operate in any environment, in any condition, without any human input at all. This level is still a fair way off. Zoe 2 is a level 4 automated vehicle. This means it is capable of self-driving in defined areas, with the driver or passenger being able to take manual control when they want to. Zoe 2 combines automated technology with connected technology, so it drives itself, but can also interact with other connected vehicles and infrastructure on the road, so it can take corrective action based on the messages it receives about its environment. Zoe 2 is packed with a variety of sensors, such as LiDARs, radars, cameras, and several computers. These systems work in real time to perform 3 core functions. Some of these systems help with localization, informing the car of its location within the overall environment.
For pinpoint localization on the road, Zoe has 3 distinct and independent systems. First being GPS-based, which is satellite-based, and it provides Zoe with an accuracy of within 2 to 5 centimeters. Second being SLAM, simultaneous localization and mapping. The car has a LiDAR on top and it maps the environment, and when it navigates through that environment, it triangulates and very accurately locates itself. And the third one is a stereo camera in front of the car. When the car is traveling through tunnels where you don't have a satellites, nor you have a distinct available points around the tunnel, in that case, we can command the stereo camera to maintain itself within the road lane.
Closely linked are systems that help with perception. This helps give the car a better understanding of its immediate surroundings.
Zoe, once it knows where it is in the environment, now it needs to know what is happening in that environment. To understand that, Zoe has a fairly sophisticated perception system. Again, it has 3 totally independent perception systems. First being based on the LiDAR, which is laser-based. Then second one is a vision-based camera. And the third one being is a radar, radio-based sensors. Based upon the information it's collected from these 3 sensors, Zoe identifies various objects around about it and then classifies them based upon the nature of those objects. For example, it is one thing to identify an object, but then to classify that as a pedestrian is another matter.
Once the system for localization and perception are at work, Zoe 2 really starts taking automation to the next level. Path planning and control now kicks in and starts calculating what action the car needs to take to achieve its future trajectory. Then begins instructing the car to take automated corrective action.
Through localization system and through perception system, car now knows where it is in the environment and what is happening around about it. Now it looks into its hard drive where a high-definition map of the environment is stored. The high-definition map has all the information about the road's speed as well as any other intersection that it is approaching. Based upon all that information, the software algorithm will start calculating what is the projected trajectory of the car and various objects around about it. Based on that calculation, car now decides how much steering angle it needs to give, or acceleration, or the brake, and proceeds further.
While these technologies work very well, they are not perfect, and therefore you'll notice two rather large buttons in the center console. These are just some of the safety measures built into the vehicle, allowing the driver to interrupt its automation and take full control.
The car right from the beginning was designed as a research platform. And as it's a research platform, the car has several built-in safety measures. First one being the driver can decide any time and apply gentle pressure to the steering or the brake pedal or the accelerator pedal, and the car will hand back control immediately. Driver can also choose to press the red button. That would apply an emergency brake and stop the automation. There is also a yellow button. If that button is pressed, the car will apply a gentle emergency brake and will hand back control. Moreover, there is a remote control. Through this remote control, the car can be stopped remotely.
Authorised by the Queensland Government, William Street, Brisbane.
Thanks to this wonderful platform, the chat for cooperative and highly automated driving safety study is exploring how this type of vehicle can be brought on Australian environment. And we are looking at several directions. One related to the driver, how the driver interacts with the system and how does he react to hand over or take over task. The second one is about the interaction with other road users, meaning what are the specificities in our environment with respect to what can happen overseas that obviously is not managed by overseas companies. The last one is looking at how this kind of technology can benefit from existing digital infrastructure, thanks to projects being conducted in parallel to this one, such as the ICVP pilots in Ipswich. Okay, move to the next slide. So the very first, and you can use this QR code to access to the final report which has been delivered. For the first part, we looked at how drivers react in an automated vehicle and how they especially react during the transition phases with the automation. And it was a real first worldwide that we engaged with a very large number of participants, 72 participants, to be able to drive sort of the Zoe 2. So they were seated in the driver's seat and they had to interact fully on the automation. I was mentioning it's a world first because it was a very long experiment that was not conducted on a driving simulator. It was conducted on a car, on a test track, but then the driver has to react to several different situations during a more than 30 minutes drive. It was tested under several conditions, and for those who don't know what Brisbane looks like in March, we experienced several severe rain, some of them where we even had to stop, but we thankfully managed to do all the experiment. We have recorded a huge amount of data, and we have looked at participants through pre and post questionnaire, but also through data being generated by the vehicle During the experiment, we were recording their action on the actuators, on the steering wheel, on the pedals, should it be the accelerators or the brake pedal. And we look as well at their gaze direction to understand how they managed to rebuild an awareness around the vehicle during the takeover demand. So in order to describe very briefly what happened during this experiment, but as I say, you can have more detail with the final report. During this 30-minute drive, there were several locations where we started to have takeover requests. And as Amit was mentioning earlier, this is a level 4 vehicle. So as being a level 4 vehicle, the vehicle can stop by itself in case of emergency situation. And in our case, we wanted still to engage the driver. So we were requesting the driver to see whether he wanted to react to the takeover request. And if the driver reacts, then the vehicle continue on its path with the driver driving the vehicle. And we were able to analyze what the performance of the driver during this part of the drive. If the driver doesn't react, and it happens several times, then the vehicle engaged by itself a minimal risk maneuver, meaning that the vehicle diverts and swerves slowly on the side of the road where the vehicle can stop safely. Once the vehicle stops, the driver had to fully take over the control, otherwise the vehicle didn't restart. So have a look at the results on this final report to understand, to have a better, more detailed information about what happened during the experiment. And this is really not a technological development that has been conducted. It was to understand really how the driver reacts and to help with the Queensland government to help the understanding and to facilitate the understanding of the transition between the automated driving and the manual driving in order to inform future policies. I can go to the next slide. So the second part was about the CITS and automated vehicle and for integration in order to understand what are the capability and benefits. As I was mentioning, it was conducted in parallel to the ICVP project. So the ICVP project for Ipswich connected vehicle pilots, led by the Department of Transport, investigates several use cases related to vehicle to infrastructure communication. And we have not replicated all use cases. We focus on 2 use cases that have been selected. The first one is related to the integration of the traffic light signal phase in the vehicle by looking at how vulnerable road user may or how automated vehicle may benefit from these messages to better interact with vulnerable road user. So the idea that we had is we sign the existing spam messages emitted by the traffic light. There are some field related to whether the traffic light phase change was generated normally or was generated by a pedestrian button being pressed. And in that case, we were using this information to react differently depending whether a vulnerable road user was likely to appear on a pedestrian crossing. But in order to make a bit of complicated approach or to make a scenario which was a bit more realistic, what we envision in this scenario is that we have a limited visibility about what happened in the pedestrian crossing, at least at the beginning of the scenario. Obviously, when we approach the traffic light, the visibility in the intersection increase and the visibility of the pedestrian crossing increase. And so a normal automated vehicle would have been able to detect the pedestrian. However, a connected and automated vehicle will then be able to infer, thanks to the messages being transmitted by the CITS system, will have been able to infer the presence or the likelihood of the presence of a vulnerable road user in the intersection and therefore reacted differently. The second use case that we envision, we signed this project, was the interaction with roadworks. So still keeping the existing CITS messages, meaning that we have not diverted from the standard of the CITS messages. We have identified that there are several fields in the DNM related to the roadwork, which relates to alternate path through the roadwork area. Because when you have a roadwork, you may have a lane which is obstructed, and when a lane is obstructed, usually the road manager created around the roadwork area a different path, and these different paths need to be transmitted to the automated vehicle so that the vehicle can react. Obviously, when you are on a multiple lane road with one direction, this may look quite easy, as the vehicle may be diverted to an adjacent lane which is going into the same direction. If you have in a rural area, for instance, just a dual lane carriageway, not separated one, then it might be more complicated, because then the vehicle will have either to deal with the incoming traffic, but then you may have mobile traffic light, or the lane may be diverted toward the shoulder of the road. And in that case, there is no way that the shoulder of the road would have been already mapped in the vehicle, and the vehicle couldn't envision having this space in order to drive safely. So thanks to this optional field in the DNM messages, we are able to create a path for the automated vehicle to approach and to manage its trajectory around roadworks. You can go to the next slide. And the last cases I wanted to develop about this cooperative and highly automated driving safety study is the interaction with other road users. In fact, it was a quite large sub-project to the chat project, which investigates what are the specificities of the Australian environment, which are not taken into account when we are looking at overseas development of automated vehicle. And just to cite some very simple example related to that, we can have, for instance, specific wildlife that need to be understood. And as Amit explained earlier during the video, it's not only required to detect obstacle, but it's far more clever to be able to understand what this obstacle is in order to predict its future path. So if you know that something has very specific movement in the environment, it's easier for the path planning to define future trajectories which are safe and which will not interact with object being detected. So from internal and from national review, we have selected 13 specific scenarios in Australia. And obviously, I already said it, but one of them is related to wildlife. We have a staggered line. We have plenty of this type of scenario which are seen in Australia. And in order to make sure that our scenarios are very specific, but also to help us and having a better understanding about which scenarios are critical in terms of road safety, but also critical in terms of impact on how this scenario can, on what this scenario can have on the deployment of automated vehicle. We then reach several experts internationally in order to get their opinion about what are these very specific cases. And lastly, can go to the last, yes. We've selected 3 Australian specific scenarios which have a road safety and deployment impact on automated vehicle. So one of them being the wildlife scenario. So obviously it's what we simply call the kangaroo case. The other one was related to road train. So if you don't know what road train is, just imagine when you have a very large semi-trailer with two trailer, prime mover with two trailer. This looks small compared to a road train. A road train can have multiple trailers, and they are quite often sited in rural region in order to carry and to transport cattle, to transport grains, or to transport minerals outside of the mines. Last scenario, which is also unique to Australia, is when you have limited one-lane road where drivers can drive on two directions. And obviously, this last scenario is not only related to how you detect the environment, but how you need to manage the interaction with other road users, because there is a lot of rules related to how people interact on this type of roads, and they are very unique to Australia. You can go to next. Yeah, thank you. And how we investigate this scenario, thanks to the Zoe, we use this vehicle in order to create a database and to record this different type of environment and to help us understand this different environment. So thanks to all of this LiDAR, camera, radar, and localization device, we created a huge database on which we try to specify what are the very specific scenario of interest and extract some atomic use cases or atomic scenario. By atomic scenario, for instance, when it relates to road train or when it relates to long vehicle, is how do we interact as a Zoe, for instance, when we follow, when we are followed by, when we overtake, and when we are overtook by this type of truck, in order to describe the very high-level data about the interaction and to be able to create prediction, for instance, around the future trajectory of this vehicle when we have to interact with them. Can go to the next slide. Yeah, and the very last part of this project is about raising public awareness. And we raise public awareness and we develop specific messages by deploying this vehicle in several areas. So we have conducted so far 4 demonstrations. One in Shaler Park when the vehicle arrived, one in Bundamba, which is an area on the west of Brisbane, and 2 in a regional settings, one in Bundaberg, and the last one that you see my background in Montisa. We are also doing static display in order to have a better interaction with the public, and we are conducting during the static display and the dynamic demonstration with the public awareness survey. And you can see on the very last picture, on the very last picture, we have a nice participant here. It's a mannequin on which we have mounted a camera, 360-degree camera that we are using in order to during the static display to engage with participants so that they can experience the dynamic demonstration, even if they are not in the vehicle. Can move to the last one. Yep.
In March 2020, the Queensland Department of Transport and Main Roads ran public demonstrations of a highly automated vehicle in Ipswich. These demonstrations were designed to test the public's attitudes and trust of emerging vehicle technologies. The demonstration showcased how automated vehicles navigated real-time traffic and other applications like summoning a robotaxi through a phone app. Overall, 73 public participants experienced automated vehicle technology firsthand.
So yes, Amit, do you want to read this one with me or to go through this one with me?
Yes, so yeah, Chad sort of is quite a different pilot than many others. And the main reason being is that the platforms that we have and the database we have in the backend, it allows us full access to every bit of data that Zoe collects, as well as all the algorithms besides just one safety critical algorithm. Everything we have access and we develop ourselves, associated artificial intelligence as well. So so that sort of gives us a lot of control and good understanding by opening the black box of automated driving system, ADS, what it is like and how they can be difficult sometimes and how they can be very computer-like, not human-like at times. So that gives us a lot of insight into that. I think that's about it, Sebastian.
Yeah.
We have some other pilots as well, but we don't have time to talk about it. There's remote operation centers and all those things we're also doing in the background. Thank you.
Okay, great. Thank you, Amit. Thank you, Sebastian. Very great presentation, insightful, and particularly, because you presented the result of the trial. It was really interesting to see one of those. So I can see two comments and also questions in the chat box. One of them is about how actually LiDARs are expensive. And Amit, I think during your presentation, you mentioned that there are two approaches for autonomous vehicles. One is vision-based, which is Tesla actually pursuing just with the image and camera. And then the other one is similar to what you have in Zoe, that you can also help get help from LiDARs, etc. And so the question is that considering that LiDARs are expensive now, which may not be good for popularization of autonomous vehicles, is there any alternative approaches for reducing the cost so far? So I think also it again comes back to your finding that if we're gonna go with the just vision-based automating, then we need to do lots in terms of infrastructure improvement, like visibility of line markings, etc. So can you elaborate more on that as well?
Yeah, sure. So when it comes to looking at the price of LiDARs, they might be expensive now, but they wouldn't be for a long time. Let's go back just a few years ago, 20 odd years ago, there was large projection TV and people were paying $10,000 for it. And now you get LCD TVs, 75-inch TVs, and you pay probably $1,000 for it.
I can as well relate when I started working in this area in 2000, having a radar mounted on a vehicle would have been an expense of above $80,000 just for having the radar and processing unit attached to the radar. And now, whatever modern car equipped either with AEB, automated emergency braking, or ACC, adaptive cruise control, they have a radar. And this option is not costed $80,000. It's costed now less than $500. So whichever technology, it's always a matter of popularizing it and making it available for most of the people.
Yes, so economy of scale, right?
Yeah.
Yeah, so whatever technology actually dominates the market, then the economy of scale would drop the cost.
And yes, and just related to the first part of the comments, using camera only raise a lot of concerns related to functional safety. The basics of functional safety is that you have to make a system redundant, but especially not capturing the information the same way, because the system may fail exactly in the same way. So if you only have camera and you have something that perturbates your camera, then you can't operate in automated mode. But if you have other sensors that can help us and that can say, okay, the camera is not working at the moment, but we still have the radar and the LiDAR that is operating. So maybe you are not going to operate exactly the same way, but you still have sufficient information to operate and to operate safely.
Okay. And also there's another question, are you planning to move towards autonomous or some trials in for buses, or I also may ask for trucks as well, because now we are kind of testing if our roads are ready for passenger cars, but I would say like for trucks, some of the geometry design elements may also change that for the passenger car, you may not be able to detect it. So yeah, the question was that particularly because the shortage of bus drivers and also was again add truck drivers may also kind of justify moving towards those pilots. Do you have any plan in TMR, Queensland TMR, or in QUT?
I can speak from TMR's perspective. No, we don't have plan for any bus or truck trials at the moment. I'm aware of some trials that New South Wales is planning with bus.
Yes.
From QUT perspective, you have my email address. If you want to fund some trials related to buses and trucks, very happy to do that. Contacted me, and we will see what we can do. But obviously, it's very related to how to do this kind of project.
Okay, great. So I'm just mindful of time, and I don't see any text there, any question. But please, people on the call, feel free to again type your question. I think Amit and Sebastian may hang around a bit further, so they may be able to answer your question, or maybe even you can just type and then I will compile it and then I will send it to Amit and Sebastian. Thank you so much, Amit and Sebastian. Thank you so much for your presentation. Okay, so I think we can move to the next presenter, who is, I believe, Sepehr Dehkordi, and Ronnie from National Transport Research Organization, NTRO. It used to be Ocean Road Research Board, ARRB. So Sepehr is going to present on the development of harmonized safety management plans for automated vehicles. So just a bit of introduction, Sepehr is a senior technology leader at NTRO, and he has a PhD in control and automation engineering and conducts interdisciplinary research in control theory, robotic, transportation, mobility, and AI. And I'm aware that Sepehr actually used to be one of the research team in QUT under supervision of Sebastian. So it's going to actually be interesting to see that how actually Sepehr kind of moved on and expanded his research at NTRO. Sepehr, would you like to share your screen? I can stop sharing.
Hi, Ellie. Thank you for the introduction. I'm very happy to see lots of familiar faces here. Let me share my screen first.
Thank you.
Okay, can you see my screen?
Not now yet. Maybe it's loading. I think you have to also click on the again another share.
Okay.
Yeah.
Let me try one more time.
Yes, I think it's loading. Yes,
Okay.
we can see that. Okay, over to you, Sepehr.
Great. Thank you very much again. Okay, good afternoon, ladies and gentlemen. So I'm Sepehr from National Transport Research Organization. And obviously, I'm going to talk about automated vehicle deployment. So let's talk about what's happening at the moment with automated vehicles. Like a big picture of having an automated vehicle is now happening across the globe. And it's critical to ensure the safety of AVs in a consistent and harmonized manner across different regions and jurisdictions. In this presentation, we are sharing some of the previous works and our thoughts on what we call harmonizing safety management plan for AVs. Obviously, in this journey, I'm not alone. Dr. Ronnie Kutadinata and Dr. Charles Carr are chief investigators in this topic at National Transport Research Organization. We also going to talk about the regulatory environment and have some examples to further illustrate the complexity and inconsistencies of various domains. This will motivate us on why we need harmonized safety management plan. Sorry. Okay, so there is a need for safety management plan for automated driving system trials. The automated driving system, what we know as ADS. Indeed, SMP must be provided as part of the applications for a trial. So what is the definition of safety management plan in the first place? An SMP is a comprehensive and structured document that outlines the strategies, policies, and procedures for organizing a trial. I put some of the examples of the trials that we engaged previously as a ARRB and NTRO. So you see that NTRO undertook several trials in Australia, and most of them was for public road. We use our usual framework, and we had that opportunity recently to use our usual framework to develop a safety management plan for other domains such as agriculture and defense application. And we see an opportunity to accelerate the adaptation of the technology by harmonizing the development of the safety management plan. Our experience in different trials shows that the regulatory environment is quite different across land domains. Some of the examples are listed in the table here. And one of the observations that we had was about the operational design domain. So if you, for example, from the experience that we have, if you consider different clusters of road, agriculture and mining and defense, we see that from left to right, we are dealing with more controlled environment. So in the road, the environment is more restricted. We need to follow the rules and the interaction between road users is higher. In agriculture and mining, there are still standards, but the environment is more controlled for operating the automated vehicle compared to the road. And in defense, the experience that we had, the environment is more controlled compared to the other clusters, and also so it's less restricted. This is the experience that we had from operational design domain perspective. We also saw different terminologies for different domains. For example, the terminology which we are using for the automated vehicles in road is automated vehicles. In agriculture and mining is powered mobile plant. And in defense is what we know as autonomous vehicle or autonomous system. Also, the technology compliance can be different. So there are road rules, there are operational design domain accreditations for the road, and for the agriculture, defense and mining, we saw workplace health and safety, which is considered by different organizations. So we have different terminologies, we have different objects, but they are actually at the end, they are the same. So the question is how we can do transition from one domain to another when we know that the terminologies are different, but the application is the same. And this is actually the subjects of harmonized SMP. So the harmonized SMP facilitates a smooth transition from one domain to another domain. So in this first section of the presentation, I want to talk about why we think harmonization is needed. Is it really important to have a harmonized SMP plan? So we try to argue the benefit of harmonization. From our experience, the SMP content is mostly the same. Also, many stakeholders are involved in one way or another in developing the safety management plan. So this makes a strong case for the harmonization of the SMP. So the ADS trial has different requirements to operate in different domains. So they have different differences with each other. And the transition from one domain to another require to define an inter-domain transition model. And this is the place that usually is a subject of argue or confusion in defining the safety management plan. Our practice shows that cohesive safety standard promote a proactive safety culture and improve overall safety performance. The benefits that we can consider is consistency, also which is about harmonizing, that harmonization promotes consistency in safety practice and helping to reduce confusion in decisions. If safety becomes a shared value and it becomes responsibility among all employees, it will lead to increased awareness, engagement, and commitments to the safety measures. Also, SMP harmonization can improve efficiency by reducing the conflict safety procedures and streamlining the process. It also can provide an environment for sharing knowledge and learning among different organizations. And finally, a harmonized safety management plan ensures compliance with legal and regulatory requirements. So by establishing consistent safety standard, organizations can demonstrate a proactive commitment to safety and the regulatory framework. The safety management plan has a major part, which is the content of the SMP. So our proposed content of the cohesive safety management plan includes several items like here, which is SMP checklist, the technology description, data for AV deployment, safety risk, and so on. I want to make your attention to number 7 and 8, which is compliance with relevant regulation and role and governance. These two SMP content may play a significant role in harmonizing a safety management plan. Compliance to relevant regulations, it's really different from one organization to another. Sometimes you require to get approval for ADS trial, but sometimes you require to get the exemptions, which is different paths to go. Also, the roles and governments involved in the stakeholders who are engaging in the safety management plan. Some of the stakeholders are involved in developing the safety management plan, and some of them are users. So they use the outcome of the safety management plan. And it really depends on the project scope and the trial scope to consider which part the stakeholders are involved. Sometimes they can be both. Sometimes they can involve in developing and also be a user of the safety management plan. A last consideration is to provide a checklist as part of the safety management plan content. And why this checklist is important, because we want to make the communication easier. We know that complexity of communication is one of the challenges to providing common sense in a project. We like that all engaging partners know their responsibility and also their expectation from each other. SMP checklist helps to avoid confusion and provides a lay language communication between different stakeholders. It includes different sections. It starts with the project scope, the objectives, the partners. It has vehicle and technology. It's about vehicle, technology, the system, and the use cases that wants to be checked, wants to be in the trial. Any safety related content, which is risk register, safety checklist, traffic management plan, incident management plan, and data availability for making decision about safety and risk register. Approval and compliance, if there is any require for approval from agency, compliance with the guidelines or any insurance insurer. And on top of that, there are relevant information such as operating details, emergency contact, incident reporting sheets, and insurance certificate of currency. So all of these are in the very beginning of safety management plan and the contents. There is also appendices, which is mostly related to training manuals, recording of training, operating manual, or any service maintenance manual, which is required to consider for the longevity of the project as well. We found that the checklist is very helpful to start the conversation and provide the high-level information for different project partners. In section 2, we try to put some of the examples that we had in the previous projects, that we saw that using the framework that we developed in the past, and we refine it every time, is kind of effective in different land domain. The first example is multiple operation domains. So recently, NTRO involved in developing the safety management plan for an Army leader follower project, and the project was about 5 trucks that they are in the convoy mode, and it's in the leader follower structure, and it goes through different domains, different jurisdictions that I will explain later. This project is between Deakin University, Australian Army, and also NTRO. And it was one of the project was the first of its kind that has 5 trucks conveying each other. The use case of the project was simulated logistic from an airfield to an army base. The project spanned in 3 different domains, which the very first one was the airport, which was a private area, and it had controlled access. There were some issues related to interaction with untrained personnel and also external contractors and subcontractors. Then it was a transition from airport to public road, and with the public road, it was lots of interaction with other road users and public member. And finally, it was a transition from public road to a military bases. Within the military bases, there were lots of there are lots of things that it's possible to control, and there is a trade-off between maximizing function and also safety of the trained personnel in the base, in the army base. Some of the consideration that we find interesting, that there was a requirement for the public road to have the escort vehicles, and these escort vehicles not allowed in the forward area in the base station. And how we do the transition smoothly from this domain, it was a subject of the understanding the safety management plan completely in 2 different domains. Also, safety driver is mandatory in public road, but it wasn't mandatory, and it was possible to remove the safety driver in the base station. But again, it comes to the safety and risk register, that in which location and where this can be done. Another example that we had and we used our proposed safety management plan, we find similarities between on-road and off-road use cases. So the first use case is a shuttle bus, and driving through the public road, and you see on the right side, it's the route mapping and route detailing for understanding the risk across the route, that the operating route. And we find that we have these different levels. We do the past trajectory planning, and then and exactly for another applications, which was for automated vehicle in feedlots for monitoring the level of the grain for the cattle, we find that for developing the SMP, we come up with for traffic management, we come up with the same route detailing. So we have feed road, we have turning points, there are share roads, there are intersection, and we have also a charging dock that the robot needs to come back to the charging dock at the end. So we have that path planning in both use cases. We have interaction with objects, either they are static and or moving. And then we do the risk analysis, similar for both concepts. And for the analysis, when we do the risk analysis, we have two options. We can treat the risk by technology, using the technology and using different sensors or developing algorithms, or we can do administrative treatment, which is about separation, isolation, or any other type of treatment. To sum up, if you want to just quickly see what is our perspective for the harmonized safety management plan, we work in all areas and we notice some parts are similar. There are benefits of harmonization for safety management, harmonization of SMP for industry, including they can operate on different operational domains. It would be beneficial for regulations, and different jurisdictions would have different regulatory domains, so they can understand each other easily. And finally, a harmonized safety management plan will simplify the regulatory requirements for the project. Ultimately, if I want to like put in one sentence that what we think about harmonized SMP is it would result in more fit for purpose operation for different domains. So it's reduced the cost and energy that you need to put for an ADS trial. Thank you very much for your attention, and I'm open to any questions.
Thank you so much, Sepehr. So I don't see any question in the chat box. Please, people on the call, don't be shy. Just throw out any question that you have from Sepehr. Sepehr, I definitely second you on that. That the safety framework should be harmonized, because even like from the previous presentation by Amit and Sebastian, we learned that, for instance, infrastructure should be ready for different type of vehicles, for different type of automation. So in that case, yeah, so we cannot really just develop it for just passenger cars, and then when it comes to buses or trucks, and then see, oh, actually, no, it is not fit for that purpose. So that was my take on it. Let's see if there's any question, and please also feel free to unmute yourself and ask your questions if you have any. Okay, so if there is no more question, again, so thank you, Sepehr, for your presentation. I believe that the next special session of NTRO, National Transport Research Organization, Australia's NTRO, also kick starts in 1 hour, but it's going to be in track 2, I reckon. So it has a different Zoom room, but we kind of separated you from your colleagues there to just have it in this session, because it was a better match with the CAF trials, we believe. Okay, so if not, then thank you so much, Sepehr. But I believe that you will stick around. So if anyone has any question, please just again type it in the chat box. I believe that's Sepehr will be able to reply to you. I don't see any public comment there. Thank you. Thanks, Sepehr.
Thank you, Ellie, for organizing this session.
Thank you. So let's move to the next one, which is going to be The potential impacts of autonomous vehicles on car-oriented population, a developing country perspective. I think that perspective comes from China. So Jinping, Tiandong, and Junxia Wang are the presenters. I believe that Junxia will present this research. Junxia is a research assistant of associate researcher Jinping Guan and Professor Tiandong. And she's also a PhD student at College of Civil Engineering and Transportation at Northeast Forestry University in China. Her main field of research are automated vehicles, travel behavior, three-phase traffic flow, emergency evacuation psychology, etc. So, Junxia, over to you. You can unmute yourself and also share your video and share your screen. I can stop sharing. Hey.
Hi, Karen.
Hi, yes, we can see your screens, so perhaps you can go to full screen mode. Awesome. Okay, floor is yours.
Okay. That team are together with Jinping, Tiandong, and Junxia to prepare for the research. It's my great honor to make a presentation. The subject of the presentation is the potential impact of autonomous vehicles on car-oriented population, a developing country perspective. I'd like to divide my presentation into 5 aspects: background, objective, methodology, results, and conclusion. Autonomous vehicles may have impacts on travel behavior and the individual's daily lifestyle. Individuals' travel mode, the urban structure, and the overall transportation system would change with the adoption of a new mode of transportation. However, few studies have focused on the impact of AVs on the car-oriented population in developing countries. This study focused on level 4 automated vehicles, which are called AVs in this research. AVs can complete the driving task and deal with the system faults under well-defined circumstances. We focus on level 4 because it is a level of AVs that is available but not widely used. AVs may have potential direct impacts on the car-oriented population compared with other means of transportation. Few studies have extensively examined the car-oriented population in the developing country. So this study aims to understand individuals' subjective options when AVs become available in a developing country. We explored 4 factors. First, self-reported pervasive knowledge of AVs. Second, the likelihood of trying out AVs. Third, the likelihood of changing from the current way of traveling to an AV. Fourth, the individual's likelihood of moving further away from the city center if AVs are available in the developing country. We also aim to find the factors that affect those 4 outcome variables and find their group differences. Unlike survey data are collected via a survey in China from October 2018 to April 2019. This survey uses simplified sampling method for gender and age. We obtained 555 valid Chinese car-oriented population samples after data cleaning. We also use 5-point Likert scale for 4 dependent variables. We have the following pivotal hypotheses to focus on in this study. The hypotheses follow the logic of the first getting to know AVs trying out and then changing travel mode. The AVs more affect residential location and moving further likelihood. However, it is unclear how many people in developing countries think that they know about AVs. In this study, we focus on 7 hypotheses. We use descriptive statistical analysis and inferential statistics techniques. The description statistical analysis is used to test the hypotheses 1 to 4. The inferential statistic techniques are as follows. Ordered logistic regression models are estimated to find the efforts of independent variables on dependent variables. T-tags on ANOVA is used to capture significant mean differences of the 4 dependent variables between 2 groups on 3 on groups. Next, we look at the results. Chinese car-oriented adult respondents acknowledged that they have little or some knowledge of AVs. The prevailing acceptance of the maximum automation's developmental level is not very high, even with lots of discussions and debates on AVs in the press. Demographic and socio-economic characteristics have great effects on individuals' self-reported perceived knowledge of AVs. Individuals whose current vehicles have traffic jam assistance tend to know more about advanced autonomous functions and convenience. Driving kilometers weekly positively predict individuals' knowledge of AVs. Attitude on perception would influence individuals' knowledge about AVs. Also, people in China are somewhat likely to try out AVs and change to use AVs. The prevailing subjective attitude towards trying out AVs are positive. The driver can do what they want because the car can complete the driving test and deal with the system faults. This condition may improve people's travel willingness and efficiency to a certain extent. Changing from the current way of traveling to an AV, the car-oriented population in China hold a positive attitude towards using and integrating AVs into their daily life, especially when one is no longer capable of driving safely. Education and socio-economic characteristics has a negative effect on individuals' likelihood of changing from the current way of traveling to an AV. The capital cost and the vehicle feature has a negative effect. Attitudes on perceptions affect the likelihood of changing from the current way of traveling to an AV. Finally, if AVs are available, then people stay neutral on whether moving further on not at this stage from car-oriented population in developing countries. Demographic and socio-economic characteristics have effects on individuals' likelihood of moving further away from city center if AVs are available. Vehicle features affect moving factor likelihood. Attitudes on perceptions of AVs also influence the likelihood of moving further away on the premise of having an AV. In this work, some variables show significant differences among the groups in the t-text on a novel, but have no positive or negative effect in the ordered logistic regression model. These variables in the t-text and novel capture additional factors that are not affecting the dependent variables, but show group differences. First, the t-text reveals significant difference in persons' self-reported perceived knowledge of AVs across different groups of beverage and employment status. A novel reveals significant difference over 5 levels of education. The t-text for the likelihood of trying out AVs reveals significant difference over different groups of gender, whether having a child or not, home-owning status, and employment status. A novel reveals significant difference over 5 levels of age and 5 levels of education. The t-text for the likelihood of changing from the current way of traveling to an AV reveals significant variation over different groups of gender, whether having a child or not, home-owning status, and employment status. A novel reveals significant difference over 5 levels of age. The t-text for the likelihood of moving further away from the city center, if AVs are available, reveals significant difference over the different groups of gender, whether having a child or not, and employment status. A novel reveals significant differences over 5 levels of age. This study conducts statistical analysis, including 4 ordered logistic regression models, t-text, and ANOVA. We observed some similar on different model results in this study compared with the previous studies. We have summarized the comparison results of the influencing factors on the above 4 dependent variables. Different groups had varying preference on AVs. In the table, males show less likelihood of trying out AVs compared with females. Females express great interest in the AV technology, while males worry about the bad driving experience brought about by the speed limit, which is consistent with previous studies. However, males prefer to change from the current way of traveling to an AV than females. Drivers with a higher educational level have more knowledge of AVs and show more likelihood of trying out AVs. However, they show less likelihood of changing to AVs and moving further away. They would consider more factors and be more cautious when associating AVs with daily lifestyle. Drivers who have a child in the household would consider the benefits of AVs that could bring to their children and be more willing to try out AVs, change to AVs, or move further away compared with no child family. Not owning a home has a positive effect on self-perceived knowledge of AVs. Those people show more likelihood of trying out AVs and change from traveling to an AV compared with others. This condition may be related to people who do not own a home, either enter a more exploring and flexible stage of life. Higher cost of one's current vehicle and time of purchasing has a negative effect on trying out AVs, changing to AVs, or moving further away.
Junxia, if you can wrap up in 3 minutes, I would appreciate because we're gonna run out of time.
Okay, it's quickly.
Yeah, thank you.
Higher acceptance of maximum automation level have a positive effect on self-perceived knowledge of AVs, trying out AVs, changing to AVs, or moving further away. Therefore, they tend to seek out and have more knowledge of AVs, try out AVs, and change the current way of traveling to an AV. The other comparison results of influencing factors and the group difference can be informed in the table. Finally, we make conclusions. Our research fill in the gaps in exciting studies on AV adoption and the potential impacts on the car-oriented population in developing countries. Urban planners and policymakers in developing countries should pay attention to those factors when preparing for the urban spatial structure change due to the shift from conventional cars to AVs. In the future, samples in the population birth year stratum of 1946 to 1955 are still limited, that we simply analyze the behavioral characteristics of the elderly. If understanding the residential location choice is the research question, other additional factors should be considered between the urban areas and the suburbs. We adopt a direct measure for AV's impact on traveling mode and moving further likelihood. Especially, we directly ask the participants the questions. This approach is helpful at this intentional stage of studying these research questions. However, the direct measure may suffer from social desirability basis on demand effects. Therefore, further study is needed to develop a more robust measurement. Okay, thank you for your attention.
Thank you, Junxia. So Let's see if there's any question here. I don't see any question in the chat box. So, well, I have one question, and is that how the finding of your research was different from developed countries? Because there have been similar surveys, I reckon, in developed countries like USA, Australia, Canada, or Europe, perhaps, on the potential impacts of autonomous vehicles. How was the finding of your research was different from those research? Did you find any unique different finding?
Lisa, could you go to the like the last page that we had the 3 conclusions? I think one of the one of the major difference that we found was the in the developed country, people may have more knowledge about autonomous vehicle, but tend to be like more cautious or conservative about like whether to adopt it or not. But in developing country, like for example in China, we do see that people may have little to some knowledge, but they're like really interested and willing to try out new technology. And that's one of the major difference or the significant thing that's in the developing countries such as China. Yeah.
Oh, okay. Yes, yeah, that makes sense. Thank you, Jenna, for the answer. Is there anything else, Gina, that if you want to add to presentation? Junxia did a great job, but I just thought.
No, I mean, it's mostly the 3 findings that was listed out at the end of the conclusion. Yeah, and this study, it did require more in-depth, another more like analysis. And we're looking forward to that, to have a more in-depth mode choice model or relocation choice model to study this topic. Thank you.
Interesting. Okay, thank you, Gina. Thank you so much. Okay, let's move to the next presentation and the last one in this session, although we will continue in the next 2 hours. The last one is on the Queensland's Ipswich Connected Vehicle Pilot, ICVP. And we have Mohammad and also Professor Ioni Louise. I know that Mohammad has a PhD. Well, you are now a faculty member of Faculty of Health, School of Psychology and Counseling, Mohammad, right?
Yes.
And Professor Ioni is an associate professor who has extensive expertise in road safety and traffic psychology research. So yeah, you can introduce yourself, Mohammad, a bit, and then you can start sharing your screen. So yeah, over to you.
Okay, so
sorry, I'm just going to share the slides for us, Ellie, but I think I need you to stop sharing the agenda.
Yes, I can stop
please. Thank you. That's all right.
Thank you, Ioni.
That's okay. No, not a problem. There we go. So just checking, everybody can see that screen okay?
Yes, we can see that.
Okay. Thank you very much. So on behalf of Mohammad and myself, who are opportunity to present, so thank you so much to the organising committee. Thanks, Ellie, and thanks to Shams. I know they're accommodating and being able to fit us into this session, so we really appreciate that opportunity to be part of today.
Thank you to you actually for contributing. Thanks.
So as Ellie's already mentioned, Mohammad and I will be talking today about what was the Ipswich Connected Vehicle Pilot, or the ICVP for short. So it remains at this point in time Australia's largest connected vehicle pilot. You can tell I'm talking in past tense, so we're talking about and reporting on all of the results today. So it ran from September 2020 through to September 2021, and we'll go over more about what was the field operational test, talking about 2 major components of the ICVP. So I'd like to start by acknowledging the traditional owners. So at QUT, we acknowledge the Turrbal and Yagara as the First Nation owners of the lands where QUT now stands. We pay respects to the elders, laws, customs and creation spirits. And we recognise that these lands have always been places of teaching, research and learning. Projects such as this is of course not possible, and I've heard other presenters talk about this as well. You know, it really takes a cast of thousands and so much support and resourcing to make such big pilots and trials possible. So very much like to acknowledge and thank the Queensland Government, Government and Transport and Main Roads, iMove Australia and QUT with support from our Motor Accident Insurance Commission, as well as the City of Ipswich, who were so kind in enabling us to conduct the ICVP in the City of Ipswich, Queensland. I won't read all the names on here, but just as an indication again of the cast of thousands that have made this project possible and all the important roles, and from our various co-authors through to members of the QUT and TMR and broader CAVI teams in TMR, as well as subject matter experts that have participated and provided important input along the way to various aspects of the pilot. So the ICVP was a field operational test, as I said, that ran for that 12 months period through to September 2021. Today, Mohammad and I will present on two major components. Although we don't mention it any further today, there was actually a simulator study component of this as well that tested use cases that weren't feasible to test on road as part of the trial. For the purposes of time today, we will just focus on these two components though, that being the on-road safety evaluation, which I'll hand to Mohammad to speak about in just a few moments, and the user perceptions and experience component of the study, which I'll talk about a little bit more later. Just very quickly, in this image, you can see very clearly there an example of one of the use cases on the HMI that was part of the ICVP, this being the advanced red light warning. You can also see the speed sign as part of the IVS speed information that was provided on throughout the trial as well. So broadly, the trial sought to answer two overarching questions. Does the system improve road safety? So what does that mean for behaviour behind the wheel and what drivers do? And is the system acceptable to drivers? So starting with the first question, oh, actually, I won't. Before I do that, I will just very quickly give an overview of the pilot location. As I said earlier, it was conducted in and around the city of Ipswich in Queensland. Overall, it was a 300 square kilometre road network that was involved and 29 instrumented traffic lights. We ended up with over 2 million kilometres of drivers travel to analyse as part of this, and 48,000 hours of driving data. So just the scope of this, you can see very quickly the magnitude of what was the trial over that 12-month period, and each of our participants contributing for 9 months of that period. In terms of the use cases, there were 4 cellular use cases that we were testing as part of it. That include roadworks warning, in-vehicle speed, back of queue and road hazard warning, as well as 2 traffic light signals, that being the turning warning with vulnerable road user and advanced red light warning. In terms of the sample, you can see here that the overall sample, we started with 355 participants, 350 who completed our baseline questionnaire survey just prior to the equipment, the CITS equipment being retrofitted into their vehicles. So I should add, these were public participants we recruited who were willing and able to have this technology, the connected vehicle technology, fitted into their vehicles for a period of 9 months of the trial. I won't go into all the details on this slide, except to say, as you can see down the bottom of the slide, by the end of the trial, at the 8th month period, where we administered the 4th and final questionnaire, we had 326 participants, of whom 323 completed. So really good continuation of participants throughout the pilot. Our sample also matched really quite well with TMR, Transport and Main Roads licensing data. So we were quite confident we had a good representation of the drivers who were involved, noting that we were recruiting provisional P2 drivers as well as open license holders. Just as a very quick snapshot of the participant conditions and hours, You can see on the graph there that essentially, as was one of the participation criteria, participants were required to drive a minimum of 3 hours per week in the test in the Ipswich area where the technology was being trialled. And generally, despite this occurring during COVID, we did have participants easily meeting that requirement. We also had conditions of an intervention group and a control group. The intervention group was either assigned the treatment first, in which they had 6 months of their 9 months with the HMI switched off, and 3 months with the HMI switched off, and then the baseline first, the other way around, the HMI off for 3 months and then the HMI on for 6 months, and the control group that did not have the HMI throughout the pilot. At this point, I will pass to Mohammad to talk through the safety evaluations and the driving data that was collected and analysed by himself and many members of the team. Thanks, Mohammad.
Thank you, Professor Ioni. During the coming few minutes, I'll take you through how did we answer the first question: is does the CITS improve the road safety? As you know, it was anticipated that the CITS warning generated by the system won't yield a positive influence on the driver behavior, which may lead to decrease in both frequency and severity of the collisions. To assess this, we come up with two hypotheses. The first hypothesis is we call it speed hypothesis, and the second hypothesis is acceleration. And if you are not familiar with the acceleration is simply, it is the summation of the absolute value of acceleration. So we consider acceleration and deceleration without any sign. The first hypothesis assume actually the normalized, the average speed normalized by the speed limit on the approach to or within the use case event is lower when the HMI is named or on. This is the first hypothesis. The second hypothesis, we assume that the value of the acceleration on the approach or within the use case event is lower, again, when the HMI is on. Next. So the data is collected in a form of trip or journey, and the journey starts when the participant starts the car engine, and the recording of the journey stops when the participant stops the car engine. However, we didn't actually analyze the whole trip. We focus on what we call scenario. And actually, our safety evaluation is focused on participant driving behavior when they encounter a use case, which is scenario. So it's a very short segment of the trip. However, as you can see here, a journey can have more than one scenario. Next. I forgot to say that, so the scenario also includes 30 seconds after the participant passed the event zone. And in the real analysis, we also didn't include all the data of the scenario. We defined something called analysis window, and this analysis window it's different from use case to another use case. And the example in front of you now shows you the analysis window we used for the advanced red light warning. And it's simply, we focus only on the segment of the scenario, which covers the restart from the time the first warning is triggered until the vehicle come to a complete stop at the stop sign. As a stop line. And we actually followed this approach or defined this analysis window because the whole design of ICVP is following FISTA handbook. And in Feasibility, all the analysis is something called event-based analysis. So we have to define a window which includes the event. We collected so many, a huge number of scenarios. However, we didn't include all of them in our analysis. We have like done many steps of filtering. The first step of filtering, we remove all scenarios which doesn't include anyone, and then we remove all scenarios which have a participant as unknown, and also we remove the first 2 weeks at the familiarization period at the very beginning of the foot, and also we remove the 2 weeks when the participant switch from enabled HMI to disabled or HMI off to avoid any residual behavior which may impact our analysis. And after we remove these 2 weeks, the unknowns, then we have a very strict data quality measures we put to make sure that all the scenarios analyzed are correct and complete and correct scenarios. So next. So our data quality check consists of three stages or levels. The first level called the CITS data health flags, and actually this these set of flags are used to ensure that the data collected from the CITS system while it was operating in a satisfactory state, which means that the GPS is available, no latency, and more other conditions which reflect the satisfactory operation of the CITS. Manual flag or operation execution is, or what we call manual flag. We use these flags to identify any known operation issues during the foot that might compromise the use of CITS system or otherwise reduce the confidence in the scenario used for safety evaluation. And the last step or level is data integrity checks, and actually we make sure that all the values are within range. We do many cross testing, which means, for example, we have the speed, we have the acceleration. So if we differentiate the speed, we make sure that the obtained acceleration should be within the same range with measured acceleration. So we did this kind of different semantic or integrated check to make sure that all the data included in our analysis are correct and complete. I should highlight that actually this doesn't mean that every scenario, every flagged scenario is removed from our analysis. Some of the scenarios are removed at the very beginning because we know, for example, if the scenario is flagged because there is a problem in the GPS, so it's very clear. This scenario we are not going to include in our analysis, but our scenarios are flagged because, for example, the temperature of the CPU is high, so we don't know what is the impact of the temperature on the measured or observed quantities. So in this case, we include these scenarios in our analysis. However, we include a regressor in our model, and this regressor will tell us if this flag has actually impact on the response or not. If it has impact on the response, on the speed or acceleration, we remove these scenarios from our analysis. This slide shows us for the number of warning for the 5 use cases. And as you can see, we have 9 warning messages available for the participant during the driving situation. And this table actually shows the number of safety warnings that were displayed for the treatment participant only. The participant who has a HMI on, we didn't include the numbers for the participant who has HMI disabled. Next, our modeling methodology is simple. So we use the generalized linear mixed effect models, but because of the strong assumption of this kind of models, actually, most of our analysis doesn't satisfy assumptions. So we had to use bootstrapping, a mixture of generalized linear mixed effect models and bootstrapping. And we defined our response, fixed effect regressor, and random effect regressors. So responses are speed, acceleration, fixed effect regressors. Of course, the main one is HMI on or off. We have participant related regressor. We have context and environment related regressors. And in order to take in our account the correlation, because of the data comes from same participant or came from the same intersection or same roadwork, so we had to add this kind of random effect regressors, and depending on the use case, we have 1 or 2 random effect in our model. So next slide, please. So in the next few slides, I'll show you the result of 2 use cases. And the first use case is roadwork warning. So we proposed 2 analysis windows. The first analysis window covers the approach roadwork, and actually it starts when the participant receive the first warning, and the end of this window is the end of the approach of the approaching zone. And the second analysis window is the window which starts when the participant receive the red warning inside the work zone until the end of the work zone. For this use case, we have 2 specific flags. So we remove any window which is less than 4 seconds, because we anticipated that actually that the participant is very close now to the event, and he sees he can see the speed limit of the signage of the roadwork. So maybe his behavior impacted not by the messages from the HMI, maybe it is impacted by the signage. So we remove these scenarios. Also, we use manual flags, and such that we remove any scenario which is collected after a roadwork is completed. After applying all the cleaning and this strict acceptance of scenarios, we end up analyzing 20% of the scenarios in the approach zone and 49% of the scenarios in the event zone. Next. This slide summarizes the finding of our analysis. So we find that there is a decrease in speed in the approach zone and in the event zone, and there is a decrease in the acceleration, which means that is in the event zone, which means that the driving in this event zone is stable. However, we found that there is an increase in the acceleration, and this is actually against our expectation. However, next slide. However, if we try to understand, is this really a bad finding? It turned out no, it's not bad finding. This has happened because actually the participant who has HMI enabled, they receive the message about the roadwork and they react earlier than the people who has HMI off. And this is why we have this increase in this deceleration. So we anticipate that this early reaction could be viewed as a positive safety outcome despite this higher acceleration. Next slide. The second use cases is with advanced light warning, and we have only one analysis window, and it's in the approach of the intersection. In this analysis, we only keep the scenarios when the connected vehicle is the first in the queue, because we don't want to include, as you know, if the vehicle is not the first in the queue, so the freedom of the driver is limited. So we remove any scenario where the connected vehicle is not in the first in the queue, and to make sure actually, because we don't have videos, we put this kind of rule. If the vehicle stopping distance from the stop line is greater than 5 meters, then we remove this scenario. It is not the first vehicle in the queue. And we analyzed 20% of the scenarios in the approach zone, and we find reduction in speed and smooth driving style. As you can see, also we have a reduction in the acceleration. Next. So in general, we find that there is a significant lower speed and acceleration for most warning. So, however, for example, for the RWH, the road hazard warning, the number of scenarios was very, very small, and the statistical modeling didn't yield conclusive finding. We have also some difficulties with back of queue because of the dynamic spatial temporal nature of the back of queue. However, we find that some evidence that actually the driver, the HMI on drivers are behaving in a smoother way compared to the drivers which with HMI. Next slide. So the final step of the analysis is okay. Well, now we need to calculate the crash reduction for each use cases. So our crash reduction methodology is simply based on the well-known Nelson power model. We adapted Nelson power model, and on each link included in our test bed, we calculated the Nelson power model reduction ratio for a bootstrap sample of the observed measurement over a link, and we compare it against a permuted sample over the same link. And we repeat this step several times such that we can decide if this reduction is significant or not. And at the end, we come up with a weighted average of the reduction for each use cases. And at the very end, we have these numbers of reduction in fatal, serious injuries, minor injuries, and all injuries types. So thank you, and the floor is open to you, Professor Ioni.
Thanks, Mohammad. So I'm very conscious of time. Thank you so much, Mohammad. As you can see, so much data, so many things to work through with the driving data that the ICVP produced. I will talk very quickly about the other component of this of the study today that related to the self-report aspects, user perception. So obviously a system can be as good as it possibly can be, but if for whatever reason people don't want to use it or don't like using it, we need to know that, and we need to know what needs to be done differently. So this was all about the second research question: do users find the system acceptable? So the user perception studies actually comprised a variety of self-report methods, which included questionnaires that were administered 4 times throughout the 9 months a participant was in the ICVP, starting at a baseline Q1 before the treatment, technology was retrofitted in their vehicle, again at 3 months, 5 months, and 8 months. We also had individual phone interviews that we conducted at 3 different phases throughout that 9-month period. And we had a final collection of data through focus groups once the equipment had been removed. So I'll talk very quickly about each of these methods and findings from them. So in terms of the survey, very consistent with literature and evidence in terms of theoretical frameworks that inform the types of measures that we use to enhance the comparability of our findings to other studies around the country and indeed the world. And so just as an example there is one of the attitudinal measures that we had in the questionnaire that was repeated 4 times, I should add that. We also had the individual interviews, as I said. Overall, of the total 326 participants that we had provide data throughout all 4 surveys, we had a subsample of those also participate in 10-minute phone interviews. It was a semi-structured interview schedule that we adapted as those 3 phases were conducted. We really saw it as an opportunity to explore, as people were experiencing the technology more, what did they find good about it, what challenges were they facing, et cetera, et cetera. We complemented that, as I said, with the focus groups, which comprised 47 participants over 14 groups. And as I said, these were after equipment removal. And we saw this particular study as our opportunity to get last chance information about people's experiences with the technology and once it had been removed from their vehicles. Key findings, very quickly. All 3 user perception studies indicated to us, when we looked across the findings from all 3 methods, that our participants had been positive about the ICVP, the equipment, and CITS more broadly. There was a slight decrease in acceptance associated with HMI use, but generally speaking, across the 9 months, we didn't see a lot of shift in overall mean scores across those various measures, and they remained on the higher side, on the above average acceptance levels over that 9 months period, which we took as very encouraging. We also found that, generally speaking, older adults reported greater acceptance than younger adults to the technology. And overall, we found most positive experiences that participants were reporting back to us was through the speed alert warning or use case. Again, all of this suggested to us they were generally positive about all warning types. As Mohammad alluded to, something like road hazard warning, there was relatively few of those. So participants' experience was limited by the fact they didn't necessarily experience a lot of those. We found that people were talking about wanting greater control of the system features. This was a pilot, the system had to be standardized, but going forward, participants were keen to see greater integration into their vehicles, more control over things like the volume of the system and the HMI screen brightness, and efforts to improve warning timing, particularly related to the advanced red light warning. I think this might be one of my last slides. Additional findings from the focus group said that participants really thought that offering some personalised feedback would be helpful. From all this data, could they be told and had some information shared about their driving performance, and that they were very willing and to contribute their data to connected technology systems to make them as safe as they can be going forward. In conclusion, the ICVP suggested to us from the behavioural data as well as the self-report positive safety impacts of the technology, enthusiasm of the public to participate in pilots and to engage with this technology, and that we have no reason to believe that future rollout of this technology more broadly would not be well received, given some further system development and refinement as we talked about. That's it. That was a very quick overview of the self-report, but happy to answer any questions or comments should there be any.
Hey, thank you so much. Thank you, Ioni and Mohammad, for a great presentation. We actually ran over times. I had a few questions, but I'd rather actually text it to you, or I will actually type it here. So if you will hang around, then I have a few questions. And also I encourage everyone else, if you have any question from this study, this great study, then please just continue typing in the chat box. Otherwise, then let's just move to the next presenter, because in this session, which actually we had to start 5 minutes ago, we have 5 presentations. So I would urge all presenters to wrap up within like 20 minutes, so that at least we have like 5 minutes of Q&A, so we make all 5. So the first presenter is Jooyong Lee, and Jooyong will present a paper on shared autonomous vehicles for efficient evacuation of vulnerable populations. Jooyong, don't you mind if you start with introducing yourself and then sharing your screen? Over to you.
Hello, can you hear my voice?
Yes, loud and clear.
Yes, hello. This is Jooyong Lee. I got my PhD from University of Texas at Austin, and this is a work that I've done with Dr. Kara Kokelman when I was working in a PhD course, and currently I got a faculty position here in South Korea. And well, many of you might know in this Eastern Hemisphere that a strong typhoon has already passed Japan and is coming straight to Korean Peninsula. So the work that I've done on the other side of the world might help us here in the Eastern Hemisphere as well. So let's get started on this presentation. The title is Shared Self-Driving Vehicles for Efficient Evacuation of Vulnerable Populations. So in evacuation situations, private vehicles are definitely preferred over any other modes due to uncertainties, independence, and privacy reasons. However, some groups who do not have any vehicle or have insufficient number of vehicles must rely on non-household transportation, which are the target of this research. For them, shared mobility can be a good option since the evacuee's location is reported in real time during pickup and drop-off calls. And fewer vehicles will also be needed since vehicles can be shared. Also, AV technology has advantage to be used in evacuation since the human driver is not under risk. Additional seat can be occupied by the evacuee, and those who do not own a vehicle may not have a driver's license, or they may be disabled or physically impaired, so AV technology can benefit them. Thus, the sum of shared mobility and AV technology, which is shared autonomous vehicle, has potential to be used in evacuating the vulnerable populations. However, evacuation shows, I would say, an asymmetric travel pattern, which means that there's many origins from everywhere, but a few destinations that are perceived to be safe evacuation destinations. This kind of asymmetric pattern affects SAV operation by high VMT, vehicle miles traveled, long waiting time, low chance of dynamic ride sharing, and requires a large fleet size. So to make this pattern back to symmetric case, a combination of SAV and a special evacuation bus operation is suggested. In this structure, the SAV serves the first mile connection from the origin to the bus station, and the evacuees transfer from the SAV to the bus, and then they will evacuate using the bus to their final destinations. So let's talk about the network and demand. It's the Houston network. The study area is made of 50 5,200 TZs and about 36,000 links, where about 7 million population live across 8 counties region near the Houston and Galveston. So we have to focus on here the island named Galveston, which is a quite vulnerable area in this topic. In this region, only the residents from the 5 hurricane wind risk zones, as colored in the left figure, will evacuate, where the zone 1 is the nearest one to the coastline, which is the most vulnerable. And overall, about 13% of the total residents are subject to evacuate here in this Houston region. And the other residents who live outside of this risk zone are colored white, and they will maintain their 50% level of their daily weekday traffic and serve as the background traffic in the simulation. And we are trying to evacuate them to the 8 exit points, which are the flags at the left figure. And these exit points are obtained from local metropolitan organizations' evacuation route map. To operate the special bus, its station location should be allocated, and this paper uses accessibility measure to find out where the bus station is located. So the link with the highest accessibility will be chosen as the location, and 1 station per county is assumed. But for Galveston, here, let me focus again, this island, since there's a bridge, the I-45 highway bridge, that will be a major bottleneck to evacuate the residents from this island, so that an additional station is assumed for that island. And this equation here shows how the accessibility of a link is measured, which is a weighted sum of links population and the travel time. So let's sum up the 6 bus stations location. This circle locations are the bus stations where it gave the highest accessibilities per counties. And to facilitate the bus operations, the 8 destinations are aggregated if they are located close together. So if the exit points are aggregated, the bus travels to the closest destination first, drops passengers there who wants to go to that destination, and then moves to the next closest destination if there's someone still on board. To sum up, there's a total of 6 bus stations, 5 aggregate bus destinations, which makes up a total of 30 bus lines in the network. And the departure time distribution assumes a staggered random departure time distribution. So for zone 1, those are the most vulnerable one. So they will evacuate at a random time within the first fifth of the 6-hour duration. For zone 2, they will evacuate at the random time within the second fifth of the 6-hour period. And for zone 5, they will evacuate at a random time during the 6-hour period. And the assumption of this 6-hour was derived from a previous evacuation order where the mayor of Galveston ordered their residents to leave within the 6 hours period. And we have to estimate who are the no vehicles available population. And we've used the population data we've obtained from the US Census Bureau. So this population data was estimated in county level. And the figure here shows that Brazoria County's census data. And the table on the left shows the distribution of household size, so that the household size can be sampled from this distribution. And from that household size, the number of vehicles owned by a household. For instance, for the household with 3 persons, using this data here, we can estimate how many vehicles are in that 3-person household by sampling randomly from this distribution. So let's sum up about the no vehicles available population. We are assuming that a person weighs about 150 pounds and carries about 50 pounds of luggage, so that 1 seat per person plus a 3rd seat for luggage is required, so that for a 3-person household, we'll need 4 seats. And next, the household with insufficient vehicles can be estimated as well. Oh, sorry. To start on, we have to estimate the households that has no vehicles first. And then next, we have to estimate those with insufficient vehicle ownerships. So we'll assume that all household vehicles are 5-seated passenger vehicles. And from the random sampling, if a household is assumed to have insufficient number of seats, then the leftover household members will be subject to the no vehicles available population that needs help from the SAV system that this paper assumes. And for the destination choice, the destination choice, it's based on the logic model as shown here, which is based on the travel time. So let's start on about the traffic simulation. I'll go very fast in this part. I've used the Sumo software with Tracy customization and repeated the simulation 10 times with a 30-minute warm start. And the evacuation departure time is about 6-hour duration. And for the mode choice between the no vehicles available population have to make choice between whether they are going to the bus station using the SAV or whether they are walking. And the mode choice is shown here with this equation under the value of travel time and walking speed assumptions. And what's important is about the bus schedule. We assume that there's 2 types of departure headway schedules for the bus, where the first one is a fixed schedule where the bus departs in every 30 minutes, regardless of whether it is full or not. But the second one is demand responsive so that it departs whenever the bus is full. So the bus will leave at the time whenever one of the 2 conditions are satisfied first. And this table shows the specifications of the vehicles. We have 5, 7, and 12-seater SAVs in the simulation with the bus where there's 37 passenger seats plus 1 seat for the driver. And the status of SAV can be either idling or drive. And when it is idling, it will be located at the curbside and does not interrupt the traffic flow. The drive means that it's driving regardless of empty or not. And so that it will be matched by comparing the direct arrival time and the reroute arrival time with respect to the pickup agents, and also considering the onboard agents. So this is how the matching is performed. The SAV will perform if the difference between reroute arrival time and direct arrival time is within a certain level for all related agents. And when considering the DRS, the number of seats left at SAV should be at least larger than the household size of the agent P. And here we've assumed that there's 15 minutes maximum time for the RT value, which will be relaxed in the further discussions. And for computational limits, we'll always pick up the agent P first, so that that new pickup agent's pickup call will be located at the first in the calling sequence and orders. And if the agent is not matched, then it will be moved to a set named unassigned agents, and the agents are rank ordered by their initial call time and will be searching their match continuously in every 10 minutes. So this is how the rerouting goes. Vehicle is planned to move this, but a new agent named C makes a call, and if it fits, then this new agent's pickup call will be placed at the first of this order so that the vehicle reroutes. And if this rerouting is satisfied under this inequality condition, then this rerouting will be performed. And another scenario is, as I mentioned, the RT was fixed to 15 minutes in the previous suggestion, but we can also think if this can be variable, which is variable to the bus headway and bus schedule. So the idea is that if the bus departs, if there's sufficient time for the bus to leave, then we can rather reroute the SAV to pick up another agent. But if the bus will depart soon, then we should not reroute, but we have to go directly to the bus station. So here, this rerouting will be dynamic, which is determined by the bus schedule, but we'll have a safety buffer of 25% to not miss the bus. So this is how the rerouting based on bus coordination works. We do not know if the bus will be operated in a fixed schedule or demand responsive schedule. So both of them will be estimated first and compare the expected station arrival time of the SAV to the expected bus departure time of the 2 different schedules based on their last headway. and compare the two different values, and the smaller one, for in this example, is the value 1, which is based on the fixed schedule. So we'll use the value 1, but for the buffer safety issue, we'll assume a buffer of 75%. So we'll have a 25% of a buffer, so that use 75% of this value 1 as the maximum rerouting time for the RT-IJK variable for that agent K. So this is the pseudocode of how the SAV DRS algorithm works, and this is the overall pseudocode of the overall algorithm. So let's run the simulation. We have 6 different SAV fleet size scenarios, 3 different SAV types, and 2 different coordinate scenarios. And the no vehicles population will be evacuated based on whether they choose to use the SAV or whether they choose to use the walk mode to the bus station. And each scenario will be repeated 10 times, and its average value is presented. So this shows the mode share result for SAV versus walk. And with more seats and larger fleet size, the SAV share increases since there's more opportunities to be on board on an SAV. However, the difference becomes negligible after more than 600 SAVs are in the network. And considering the time spent on an SAV, the contributing factor to reduce total time spent on an SAV per person is the waiting time reduction. With the larger fleet size, the waiting time reduces, but once more than 600 SAVs are in the network, this reduction is negligible. However, the travel time increases with larger fleet size, but the waiting time reduction can offset the increase of travel time, so that total time spent on an SAV decreases with respect to the fleet size. And for the number of seats, it affects the total VMT, where increase of seats results in decrease of total VMT by SAVs. Since number of agents are fixed in all scenarios, reduced total VMT means that fewer miles will be needed to serve agents, implying that ride sharing is promoted with more seats. Indeed, the increase of shared VMT percent and eVMT, the empty VMT percent with respect to the increase of seats, support this hypothesis, and more agents are likely to be on board with larger vehicle size. And for the fleet size scenario, similar tendency can be observed. Specifically, the increase of shared VMT with larger fleet size means that DRS is promoted with larger fleets. Thus, a vehicle spent more time on DRS with the increase of fleet size, so that travel time increased with larger fleets, as shown in the previous slide. And this figure shows the occupancy configuration by the observations of each number of seats being occupied. The average number of household size is 1.73 people, so that having more than 2 passengers on board means it's a shared ride in average. And this rate increases from 42 to 46 and 48%, which means that with more seats, with larger vehicles, ride sharing can be promoted more. The performance of SAV system should be measured based on the average bus departure time and arrival time per person. And the figure here shows that with more SAVs in the network, the departure and arrival time, which is measured from the time 0 when the evacuation started, this value decreases, which means that better evacuation is performed with larger fleet size. But the number of seats does not seem to affect the bus departure and arrival time, so that we can conclude that number of seats affects SAVT's VMT and ride-sharing performance, but does not impact individuals' travel time. And lastly, the operation time is presented, which is the non-idle time over the total operation time. So if we have more than 600 SAVs, the operation time becomes excessively low, below 50%. If we have less than 600 SAVs, we've seen that the travel time is too longer, so that we'll conclude that having 600 SAVs, which is 1 SAV per 14 people, with all being 5-seated SAVs, is a cost-effective base case scenario. Next, the bus coordination strategy is analyzed. I'll go really fast in this session. This table shows the SAV mode share result from the coordination scenario, and when compared to the non-coordinate scenario, which is the value in the parentheses, shows that mode share result does not show much difference, although mode share slightly decreased when coordinated, but the total VMT increased, which implies that DRS is more restricted with coordination. And the shared VMT percent shows that it decreased so that the maximum reroute time is smaller in the coordination than the 15 minute in average when it is coordinated. And comparing the waiting and travel time, first the waiting time, it greatly increases with smaller fleet size, but it's negligible with more than 1,000 SCVs. But the travel time falls when coordinated because of the direct travel time. So when it's coordinated, the SCV doesn't reroute much, but it goes straight to the bus station. So that we can expect a trade-off of increased waiting time to get my chance to take that SCV. But then if I get the chance to get on that SCV, then the travel time gets lower when it is coordinated. So the result shows that bus departure, so we have to measure how the performance will be by the bus departure and arrival time. And both of them did not change much with the coordination. So what we can conclude from the coordination scenario is that the performance, the departure and arrival of the bus does not change much, but we have seen a trade-off between increased waiting time, but decreased travel time. So this can be an option if the evacuee accepts this kind of trade-off, since the performance, the overall average performance would not change much. And lastly, we've checked how the evacuee's behavior would affect the evacuation performance based on two different behaviors and assumptions. One is that the evacuee may not be willing to share the rides. So in that case, their maximum rerouting time will be assumed to 0. And also, we've assumed that we are having a staggered departure time distribution, but the evacuee would not follow that kind of assumption and strategy, but rather evacuate as soon as possible. So that it's non-compliance case or the panic case. And we've increased that kind of evacuees from 0, which we've talked already, to 100% and see how the performance changes. Here, the base case of 600 SAVs, all 5-seated vehicles, and the rerouting time of fixed 15 minutes are assumed for the simulation.
Yeah.
And
Jooyong,
for the
I'm so sorry, can you wrap it up in 1 minute? Because we're kind of running out of time.
Yes, sorry.
Sorry.
So I will make a conclusion here. Sorry for the no DRS and non-compliance case, but for the no DRS case, the waiting time increased, but the travel time decreased as well. But the problem here was that the departure and arrival time of the evacuation bus increased, so that this case is not recommended, so that evacuees ride-sharing behavior should be recommended. But for the non-compliance case, our simulation suggests that at least the bus departure and arrival reduced, so that the system can manage the evacuees' non-compliance and make up sufficient evacuation performance. So this is how we've planned to use the SAV system in evacuation. And thank you very much for listening to my presentation. Very happy to have any questions or suggestions to this topic. Thank you.
Thank you, Jooyong. Please don't be shy. Type your question in the chat box. So, Jooyong, I have one question. From the beginning, when you started presenting the idea of evacuation, I was just thinking, can you also look into that problem similar to, for instance, transit route network design? Because you're kind of just finding the location of buses or SUVs. So it could be similar to finding the location of bus stops and then the routes, etc. So what was the reason that you went with simulation and utility model for and not like an operation research approach?
Oh, yes. So basically, we were trying to not just check the evacuation performance, but we were also trying to check the network loading part in terms of transportation. So that's the reason why we've performed this sumo simulation. And that's the biggest reason how the individual links and the networks are loaded based on a vehicle, and where's the bottlenecks in terms of transportation, to identify those bottlenecks and how we can even further evacuate the evacuees more efficiently. And that was another work that we've done based on the results in this topic. So that's the reason why we've designed our topic in this way.
Okay, I see. So Gina also has a question. She said, I did not follow what are the vehicle owners doing. Do you have background traffic?
Yes, so they were the background traffic and they were evacuating from their home to their destination, but they were not tracked because in here, it's an evacuation case and having a private vehicle is definitely preferred. And I would also use my car if I have one, but there are a population who do not have that kind of option. And they are started in this topic so that those who own vehicles are not tracked in this presentation.
I see. Okay, great. No more question from Jooyong? Okay, I don't see anything in the chat box, but again, continue typing your question if you have any for Jooyong. Thank you so much, Jooyong, for your presentation. And best of luck with your new career as a faculty member in Korea. Exciting. Okay, great. So let's go to the next presenter, Xinchen. Xinchen is going to talk about feasibility study of highway alignment design controls for autonomous vehicles. So Xinchen is a PhD candidate of traffic engineering at Tongji University, and his research interests are in traffic safety analysis, safety evaluation of roadway design, roadway readiness for autonomous vehicles or automated vehicles, better say, and driving simulation. So Xinchen, I can stop sharing my screen. I have your video and
okay, I will share my screen.
Yes. Go ahead and share your screen over to you. Your video actually was disabled, so you can enable again your video. Click on it.
Okay. Thank you, Ali. And good afternoon, everyone. I'm Xinchen from Tongji University. Today, I will present our research on feasibility study of highway alignment design controls for AVs. And this paper has been published in Accident Analysis and Prevention. This presentation has 4 parts. The first is the introduction. In the past few years, various automobile enterprises have been developing autonomous vehicles, and highway test sites for AVs have been constructed in the US, China, and many other countries in Europe and worldwide. The specifications for highway geometric design have been used in most countries, but currently they are only based on the perception abilities of human drivers and do not consider AVs. These specifications mainly contain 3 sections: horizontal alignment, vertical alignment, and cross-section design. Some controls, like minimum vertical curve lengths, are based on the perception parameters, and others are based on non-perception parameters. So studies have demonstrated that perception abilities differ between human drivers and AVs. So these differences should affect the highway design controls. But when this study was being conducted 3 years ago, few studies have attempted to investigate the highway geometric design with respect to AVs. As for the perception differences, the parameters can be classified into 2 types: perception field and perception reaction time. Regarding the perception field studies, the range parameters include height, vertical angle, and range. And the most commonly used sensors in AVs include radar, LiDAR, camera, and ultrasonic sensors. And the 2 tables summarize and compare the maximum field of common sensor types. For human drivers, studies of driver's sight distance have demonstrated that a driver could recognize an object clearly at a maximum limit of 200 meters. Regarding the perception reaction time studies, the Green Book published by the AASHTO in the US recommends a perception reaction time of 2.5 seconds for design purposes, and previous studies showed that it appears adequate to cover the full range of drivers. And for AVs, 0.5 seconds was selected in previous studies, and modern computation and actuation were considered in the selection of the perception reaction time. So about the research question in their study, since the perception differences may indicate the need for different design controls, it's essential to ascertain whether the existing design controls for highway alignments are applicable to the AV. And this study aims to derive geometric design controls for highway alignments specifically to meet the circumstances of AVs and consider the perception difference. The design controls to be derived and verified include the required stopping sight distance, length of second crest radial curves, and length of horizontal curve and previous sight distance for combined alignments. The derivation methodology was based on the Green Book and the NCHRP report 600. They provide computational equations for design controls according to the fundamental physics and vehicle dynamics. And the perception differences were considered, and we adjusted the parameters in the Green Book and the NCHRP equations, and then used to derive the controls for AVs. The major design control for vertical alignments is the provision of an ample sight distance for given design speed, and it is recommended that all vertical curves should not be shorter than a minimum length that provides the required stopping sight distance. To determine these controls based on the AV's perception length of sag and vertical curves for AVs are computed respectively in this study. Firstly, the required stopping sight distance is the distance needed by a vehicle traveling at the design speed to stop before a potential emerging incident, and it contains two parts. The perception reaction distance covered during perception reaction time and braking distance needed to stop the vehicle, measured from the spot where the brakes are applied. And the table summarizes the selected values of the perception reaction time and the deceleration rate in this study. For human drivers, the current perception reaction time is 2.5 seconds, and it covers 95% of drivers. The time for AV sensing and data processing, navigation-related decision-making, actuation, and engaging of a braking system seems to be no longer than 0.5 seconds. And the deceleration threshold for determine the braking distance for human drivers is recommended to be 3.4 meters per second squared. This threshold is regarded as attainable for most drivers facing an unexpected incident, and it accounts for wet pavement, average tire wear, and inefficient use of ABS. So because these conservative assumptions also pertain for the most part to AVs, the same deceleration threshold is applied to AVs. The next is the sag curve. The minimum length of the sag vertical curve should meet 4 criteria: required stopping sight distance, passenger comfort, drainage control, and the general appearance. Our comparison is limited to the first 2 criteria due to their greater importance. For the computation based on the required stopping sight distance, the figure illustrates the parameters used in determining the length of the second vertical curve that is needed to provide a specified value for stopping side distance. The headlight height is used for the human-driven vehicles because the nighttime driving requires the most conservative stopping side distance. When a vehicle traverses a second curve at night, the distance available to be seen ahead will depend on the headlight height and the direction of the beam. So a headlight height of 0.6 meters and a 1 degree upward spread of the beam are assumed in the Green Book. And for AVs, the sensors will take over the perception responsibility. The sensor height is determined by the vehicle type and the position of the equipped sensors. And we, in this study, we assume the position of the sensor consists to the radar in its commonly located position in the bumper, and a sensor height of 0.45 meters is used according to the common sensor height and the typical bumper height of passenger cars. Regarding the detecting angle, the upward angle from the horizontal of most sensors exceeds 20 degrees. So the relatively conservative angle of 20 degrees was selected. Passenger comfort was the second criterion for the minimum length of second curves. Second curves need more attention to passenger comfort because the gravitational force and the required central petal force are in opposite directions simultaneously, and a high centripetal acceleration would make passengers experience discomfort. So according to the Green Book, the centripetal acceleration should not exceed 0.3 meters per second squared. Computation for the minimum length of the crest curve is based on the required stopping side distance, and the sensor height is the same 0.45 meters used for side curves. For human drivers, a 1.08 meter high eye height was selected in accordance with the Green Book. An object height of 0.6 meters for the tail lights of a lead vehicle is assumed for drivers in the Green Book. It is the same height used for AVs. This part shows the computation results for vertical alignments. In accordance with the Green Book, the highway design speed in this study ranges from 20 to 130 kilometers per hour, and the longitudinal grade ranges from 0 to 9%. The two figures illustrate the comparative stopping side distance profiles for AVs with a solid line and human drivers with a dashed line. The required stopping side distance of AVs and humans show similar trends with an increase of design speed and longitudinal grade. The effect of gravitational force on deceleration becomes more significant with the increased grade. For both downgrades and upgrades, since the AV's perception reaction time is much faster than humans' perception reaction time, the required stopping side distance is consistently shorter for AVs than for human drivers under the same highway design conditions. In extremely complex environments, the perception reaction time may be longer and it may be shorter in the future. The AV stopping side distance for 3 perception reaction time of 0.2, 0.45, and 0.8 seconds are calculated on a level roadway and are compared at various design speeds. And the results show that at the same design speed, the required stopping side distance decreases as the perception reaction time value decreases. And as for the second vertical curve, since the rate of grid change is equal to the algebraic difference between the secting tangent grades divided by the length of curve. So the quantity L divided by A, termed K, is useful in determining the minimum length of vertical curves. And the K is used to represent the rate of vertical curvature in the sag and crest curve design controls in this study. The sag curve design controls are listed in table. The columns on the left show the various design speeds for each of the K values, and the rounded required stop-inside distances are used in the calculations. The K values in the right columns are calculated for both AVs and human drivers. They are based on the required stop-inside distance and on the passenger comfort. And then the two types of K values are considered together as the rounded maximum K values presented in the design control columns. The sag curve K values for AVs are lower than those for human drivers. It indicates that the AV permits more tolerant design controls, and the AV's shorter required stop-inside distance and its larger vertical angle reflect the AV's perception advantages over human drivers. And these advantages result in a smaller minimum curve length for AVs. And it should be noted that the dominant criterion for sag curves differs between AVs and drivers. The passenger comfort is the absolute influencing factor for the AV. And for human drivers, the required stop-inside distance criteria takes the precedence. Like sag curve controls, the crest curve K values for AVs are also lower than those for human drivers. In Glaser's study, they conducted a field test on semi-autonomous vehicles' lane keeping performance on crest curves, and they found that the disengagement tended to occur when K values were lower than 20 meters per percent. But the design speed of the test roads range from 60 to 100 kilometers per hour, and which have lower critical K values ranging from 6 to 41 meters per percent in this study. Factors such as traffic conditions, road markings, and weather could be jointly involved in disengagement during the field test. The next section computes the design controls for complex combined highway alignments. The horizontal and vertical alignments should not be designed independently, but should be appropriately coordinated. In the Green Book, it recommends that a sharp horizontal curvature should not be introduced at or near the top of a pronounced crest curve, because the horizontal change in alignment may not be perceived in advance. And since the view ahead is foreshortened, a sharp horizontal curvature should not be introduced near the bottom of a pronounced sag curve. And due to the constraints such as terrain or cost, these guidelines are not always met. So we consider the two design situations. Firstly, when the design meets the coordination guidelines, the horizontal curve should be longer than the vertical curve. The minimum length of the horizontal curve for AVs is determined by the corresponding minimum length of the sag or crest curve. When the design does not meet the coordination guidelines, the previous side distance is used as a measure of driver side distance to ensure safety. The previous side distance sufficient for driver or AV sensor to perceive and respond to a horizontal curve ahead is applied, and it has two components. The total net distance traveled on the tangent approaching the curve, and the distance that must be seen or detected or perceived, the horizontal curve configuration. For the S1 component, it consists of two further components, the perception reaction distance and the deceleration distance. These two components should lie entirely on the tangent and should end before the circular curve begins. we assumed that the curve operating speed is slightly lower than the design speed, and supposing no emergency braking, though the curve operating speed is considered to be 95% of the design speed. The other parameter is the S2, the perception of the horizontal curve configuration. It depends on the curve's radius and its deflection angle. And in Hassan's study, the established nonlinear regression model of delta performs well on goodness of fit, so it is used in the computation. The results shows that the distance traveled on the tangent increases with design speed, and the distance that must be perceived generally increases as the horizontal curve becomes gentler, as does the distance required to produce a deflection. And for the previous side distance, it increases with both design speed and horizontal curve radius. Since the perception reaction time is the only perception parameter, so this control is shorter for AVs than for human drivers as well. Okay, to sum up, the computed highway design controls for AVs are more tolerant than for human drivers, and results demonstrate that perception characteristics play a crucial role regarding the required stopping side distance, as it increases at higher design speeds and steep downgrades, because the maximum range of the AV is illimited. The longer stopping side distance suggested for these conditions may not be available for AVs. So to avoid either reducing speed limits or limiting vehicles' individual speeds, AVs with insufficient sensor ranges should not be certified for such conditions, and their operational design domains should be limited to lower speed roads. For the minimum length of Segel crest curve, based on the K values, it is more tolerant for AVs as well. And the perception reaction time, eye or sensor height, and vertical angle should be considered as the key perception differences. And more importantly, the seg curve design controls have different dominant criteria and priorities. Regarding the combined alignments, for those do not adhere to the guidelines, the required previous side distance is the critical control. And at last, this study has two major contributions. On one hand, we provide the initial results and conclusions for highway geometric design controls that are safe and suitable for AVs. And on the other hand, because AV design controls are demonstrated to be more tolerant than the current controls, the benefits of the proposed design controls could allow higher speed limits for fully AVs, and highway construction costs could decrease. But for the present, these more tolerant design controls should not be directly applied in the current mixed traffic of human-driven and autonomous vehicles. For the future study, we should include field-based and simulated experimental observations to consider sensor failures. And also, the values selected in this study might not be completely in accordance with future characteristics. So we should give further attention to the interconnection among human beings, vehicles, roads, and environments. At last, I would like to present the recent work in Tongji, because the study presented today was conducted and published before, and some latest work has not been published yet. So firstly, we conducted series of studies on the operational design domain for AVs based on the theoretical computation regarding the highway segments. The ODD studies on both normal segments in this paper and freeway entrance terminals were carried out. And another topic is on the ODD at intersections for AVs. we have taken into account various intersection types. And since last year, we have started to conduct highway readiness studies for AVs based on field tests. The Tongji University Road and Traffic Holographic Data Acquisition System was employed on the test vehicle, and we analyzed the impacts of highway design and condition characteristics on the performance of AVs. As one of the studies illustrated on this page, we focused on the impacts of AV's lane detection performance, and we hope to present it to all of you in the next year. That's all for my presentation. Thanks for your attention, and thanks for the opportunity provided by the BTR organization committee. Thank you.
Thank you, Xinchen. Thank you. That was one of the research topics that I have so passionate for, because I think well, after finishing my bachelor's, I worked as a geometric design engineer in a consulting firm, and I was actually designing all of these horizontal curve, vertical curves for interchanges, etc. And then when I was introduced to CAPS, that was always kind of a curiosity or question that I always had, that how these attributes will change, because I know we all have read the Green Book, and we know that these formulas actually have been designed based on the height of the human driver, based on the human reaction, and then when we are talking about tasks, all of these will change for sure. So actually, I was kind of busy texting, typing questions to not just forget. And also I encourage everyone to also join me and ask questions. But I can see one question from Gina, and Gina asks that, so this implies that you're going to build highways just for AV in certain areas. But then I think my interpretation from your presentation was different. So I don't know, my interpretation was that because you would have a shorter stopping side distance, SSD, perhaps you can you don't have to modify it. AVs will be more tolerant. But over to you. Can you answer Gino's question first?
Let me check Gino's question.
So do you reckon that do we need to rebuild our highways for AVs? Do we need to change our highways, and we are not talking about, I think, on-ramp or off-ramp. We're not talking about entry to highways or exit of highways, but in terms of the vertical curves and horizontal curves, do we need to modify them for AVs?
I think firstly, in this stage, especially the mixed traffic condition, we'd better not modify the design for the such as the horizontal curve or vertical curve, or maybe we can design an AV exclusive lane for them, and also in another study about the horizontal curve readiness for AVs, they found that the deflection angle is not suitable for all the AV sensors to perceive the deflection because of the horizontal detecting range of the AV, and they are limited to some areas. So maybe we should limit the operational design domain, like these AVs should not operate on these roads or regions. So that's my point of view.
Okay, and I think I had read a few other reports or the finding of some trials, mainly in US, that they and the finding was that automated vehicles, they will have a shorter stopping side distance because they can modify their speed more frequently, and
Yeah.
also shorter decision side distance, DSD, because the reaction of automated vehicle is shorter than human drivers. Is that correct? Does it align with your findings?
Yeah, this is according with our findings.
Okay, excellent. And also just considering that different automated vehicles, the sensors have different heights. For instance, when you think about all of those like Waymo ones that they have LiDAR mounted on top of very good height. And also we saw Zoe, the trial that Amit presented and Sebastian presented. And but then we also have Tesla that they don't have any LiDAR. And I think their cameras basically, well, although actually they have also cameras at them. So, the height of the sensors are different. How are we going to accommodate that? Or do you think that automated vehicles should accommodate to our current geometric design specifications?
I think we can accommodate the AVs from different aspects. From the vehicle aspect, maybe the sensor capabilities like the range or the distance, and its techniques for the detection should be improved in the future. And for the roadways, we also should consider some demands from the common AVs, and maybe also such as the smart roads, like transferring some connected data from the roadside. I think both aspects should be considered.
Yeah, nice. Okay. Okay, so I think, oh, well, there is another question. So CU as the literature shows that many congestion caused by driving behaviors in highway curves, especially at sites. Do you think your research may further consider how to alleviate such congestion, both from aspects of AV control and alignment design?
This is another topic, I think, because if you talk about the congestion, maybe it's about like the trajectory control or the speed control strategy. But in this study, or like our operational design domain study, it's just focus on the road geometry, and maybe for the road congestion, it should consider more connections with the surrounding vehicles, and the strategy applied in the AV control, I think.
Great, thank you, Xinchen. So let's go to the next presentation. That the next presenter will be Lichen Luo, and we have Lichen. So Lichen will present the environmental impacts of private automated vehicles in the context of car-dependent regions, a case study of Gunma, Prefecture in Japan. Sorry for my bad pronunciation, but Lichen, over to you. Can you just introduce yourself a bit, because I didn't have your bio, so I stopped sharing. So now you can start sharing your screen, and also, yeah, floor is yours.
Yeah, thank you. And can you hear me?
Yes, loud and clear.
Yes, and the pronunciation is actually good. So, and actually, I think I uploaded my bio, but okay, let me introduce briefly myself. So I'm now a postdoc in Hiroshima University, Japan, and before that I graduated from the University of Tokyo in this April, and now I'm focusing basically on the some travel forecasting issues, focus using discrete choice models, and especially in the context of autonomous vehicles. And please let me share my screen. Okay. Can you see my screen?
Yes.
Yes, thank you. Okay, so thank you for having me here, and thank you for joining the presentation. Today, I'd like to present an empirical analysis titled with the environmental impact of a private autonomous or automated vehicles in the context of a car-dependent regions, a case study of Gunma Prefecture, Japan. So, and please bear with me since there are many models involved in this research, so I don't have much time maybe to talk about them in detail. And so the basic background for this research is actually as mentioned in this topic is that automated or autonomous vehicles is expected to be operated in the near future, which has the main feature that the human will see the controllability of the vehicles to robotics. So that on the top of that, autonomous vehicles could have some implications like some of them are good and some of them are not so good. So the question of this research is that how about the impact on emission? So on this slide, I'll give you a brief summary of the relationship between AVs and emission effects, and please consider it as a brief literature review for the emission implications in the context of autonomous vehicles. So in our exploration of greenhouse gas emissions, it's evident that the transportation sector plays an important role. Specifically, in 2019, this sector accounted of the fourth largest contributor to global greenhouse gas emissions, and with a substantial 70% stemming from road transport. So considering the urgency of the climate change, the coming 2 decades necessitates rapid decarbonization with a particular emphasis on the transportation sector. So as we all probably know, that a promising solution in these domains, the integration of case, which represents connected, automated, shared, and electric vehicles. So research, for example, from Austin, Texas, indicates that a potential benefits a project around 40% reduction in CO2 emissions by 2050. And it is noteworthy that this substantial reduction is closely linked to the transition towards renewable energy sources, according to the authors. While a crucial consideration in this discuss is the choice between private and shared mobilities, private automated vehicles, abbreviated hereafter as PAVs, offer benefits in urban accessibility and environmental impacts, but to a lesser extent than shared mobilities, according to the existing literature. So to illustrate, a study conducted in Portugal demonstrated around 21% CO2 reduction with shared automated electric vehicles as opposed to the private ones. Yet, it's essential to consider societal inclinations. So according to 2 studies based on SP surveys, so PAVs still is considered advantageous in terms of in-vehicle time use efficiency, and they're observed more preferable over SAVs. So as Wadud and Mattioli, and in 2022 addressed, a near total transition to automated ride services is not a foregone conclusion. So as such, in this research, we'd like to address our research question as what is the impact of a PAVs on the total distance traveled, and on the top of that, how do the greenhouse gas, which is separated as GHG emissions, and the air pollutants resulting from the introduction of PAVs compare to the existing governmental climate pledges. And to do that, the figures in the right side in this slide illustrated the 5 steps of the analytical framework applied in this study to address this problem. So by incorporating multiple steps and modules, the framework allows for a detailed understanding of the complex interactions between transportation, energy, and the local environmental protection goals. So firstly, we characterized our case study analysis in Gunma Prefecture, which I'll introduce later. And this involved in collecting, of course, the data for the initial travel demand in this region. And secondly, a baseline and 4 plausible alternative scenarios to account for the uncertain future were designed, consider the different trends, and especially consider a value two main variables: the value of travel time and expansion of electrification on the passenger vehicle fleets. And given uncertainty about the future passes of the power generation sector in Japan, we also conducted a sensitivity analysis to consider 3 different tendencies of nuclear power and renewables in power grid by 2050. And thirdly, we modeled the travel behavior individuals in the case study area. This included analyzing data on the travel patterns, mode preferences, and other choices. And fourthly, we developed a typology projection until 2050 of the various types of vehicles. So to identify the different powertrains and the fuel efficiency for the vehicles to be implemented to be deployed in 2050. And finally, in the 5th stage, we evaluated the energy and local environmental impacts of the scenarios designs with consider that the previous 3 modules as for the year of 2050. So to the best of our knowledge, there exists a distinct research gaps within the domain. Here, I'd like to briefly talk about the research originality of this research. So our study aims to address and narrow the steps, the research gap, like first of all, the studies conducted with PAV in emission context is relatively limited, and especially induced travel demand resulting from PAV introduction has not been properly accounted for emission calculations. For example, many of them from the existing literature consider that using current travel demand levels, and some others rely on exogenous assumptions or calculations. Furthermore, research combining LCA analysis in the travel behavior modeling in the context of AVs is still limited. So LCA stands for Life Cycle Assessment, which allows for a more comprehensive evaluation of the environmental impacts of vehicles throughout its entire life cycle. So going beyond the vehicle level, which is shown here with the red box, and considering the upstream processes such as the vehicle production stage and the fuel production stage. Finally, we think also to add data points to the research in the context of Japan is also important for as one of the research contribution of this study. So we choose Gunma Prefecture, which is a landlocked prefecture located approximately 100 kilometers away from Tokyo as our study region for this research. So the region spans an area around 6,000 kilometers square and accommodates a total population of around 1.9 million inhabitants as of year 2020. And Gunma can be accurately featured as a region that heavily relies on private automobiles for transportation, as the prefecture has the highest average ownership for private four-wheeled vehicles in Japan, with around 70 vehicles per 100 persons. And like other prefectures in Japan, Gunma has been dealing with aging issues. As of 2022, around 26.5% of Gunma population are over 65 years old. And besides, according to the Gunma's environmental white paper in 2022, the prefecture has set a goal to achieve net zero GHG, greenhouse gas emissions, by 2050 to reduce the emissions from the transport sector. The document especially mentioned that they'd like to promote the use of electric vehicles, including fuel cell electric vehicles and battery electric vehicles. As such, we consider Gunma directly applicable and suitable for the research objectives at hand, and that focus on the implication of private autonomous vehicles. Sorry. And then each scenario here we show you that 1+4 scenarios with each stands for different future image. So our standing point is baseline trains that considers only human-driven vehicles, and but incorporates the population decline. So total population in 2050 was set to around 76% of the current population in Gunma. So, and for the other 4 alternative scenarios, we firstly assume in all of them that the households who own HV would switch to PAV, which translated into around 20% increase in the road capacity compared to the HV. And as a result of that, we then think about the various characteristics for the 4 alternative scenarios, accounting for different levels of value of travel time and the level of electrification in 2050. So scenario A presents conservative assumption in terms of the 2 variables. The share of the new electric vehicle sales from 2020 to 2050 follows a modest growth as announced by the current policy of the Japanese government. And accordingly, the battery and the plug-in electric vehicles represent around 25% of the total travel demand by 2050. And the scenario B, on the other hand, considers a more optimistic set of vehicles of travel time and the same share of the new electric vehicle sales as scenario A. The scenario C and D on the contrary assume the same values of travel time as scenarios A and B, but consider a high share of electric vehicle sales. So basically under the assumption, like the Japanese long-term strategy of net zero emissions, we assume that in scenario C and D, all new sales will be electric vehicles and none of them will be like in, for example, conventional gasoline vehicles. And to better reflect the possible nuances of the Japanese government's energy policy and the current situation of the nuclear power generation following the accidents at the Fukushima nuclear power plants, sensitivity analysis was also conducted to characterize 3 different energy mixes by 2050. So we come up with 3 options. First, a pre-Fukushima power generation mix, assuming a return to the energy plan in place prior to the nuclear incident. And the second, a moderated combination of the nuclear energy and the renewables that aligns with the present states of the affairs. And thirdly, an ambitious population of the new renewables in the power grid reaching around 80% by 2050, and no nuclear power plants are online. And as for the travel behavior modules, we basically follow our one of the previous papers that's conducted by the authors in the previous year. So the model system considers 2 modules pertaining to the transport domain: an activity-based travel demand model DAS by Bowman and Kiva in 2001, and an agent-based dynamic traffic simulation model, MASSIM, which I think both of them are quite well known in the transportation field to evaluate the transport demand and the supply parts. So the 2 modules were integrated to capture the short-term travel demand supply interactions, and which we think is important in measuring indirect effects such as the travel congestion due to the induced travel from the PAVs. And here we show you how we calculated the fleet, the share of a fleet topology of the passenger vehicles in the study region. So we estimated it based on the recursive simulation model, considering the historical and future trends of the new vehicle sales and the survival rates. So for the future trends, the new vehicle sales shares, we considered conservative new sales of electric vehicles as defined in scenarios A and B, and high sales as defined in scenarios C and D under the suggestion by like the net zero emission strategy by the Japanese government. So as a result, under the conservative assumptions, gasoline and hybrid vehicles represent a share of 98% of the new sales in 2020 and linear fall to 75% by 2050. On the other hand, but following the net zero emission strategy, conventional gasoline and hybrid vehicles new sales share declines to 0 in 2050, and which is substituted by the battery electric vehicles and the fuel cell electric vehicles with a share around 95% and 5% respectively. And the life cycle assessment analysis used in this study also merits some information here. So the target for the LCA life cycle assessments in this study involves the consumption of fossil fuel resources, greenhouse gases, particulates matter under 2.5 and the nitrogen oxides and the sulfur oxides. And the system boundary of the analysis encompasses both the fuel production, so-called wheel to tank, and the driving of the vehicles, commonly referred to the tank to wheel, and also the manufacturing of vehicles is included in analysis, while the end of life, like the reuse of the batteries in electric powertrains, is beyond the scope of this study. So basically, we use the grid model to do the LCA assessment for this study. And now I'd like to step into the results of the simulations of this study. So this slide reviews a summary of the results of the travel behavior module for year 2050. According to the results, we found that increasing the total distance travels range from 29% up to 48% compared to the baseline train. So this range is within the upper bounds of the results reported in the existing literature. So we argue that the new PAV trips resulting from the model shifts and the induced travel demands, for example, from those who cannot drive, contribute considerably to the observed increases in the PAV distances compared to the cases that people use HV. And as for the consumption of fossil fuel resources and the life cycle greenhouse gas emissions, we show you here with two figures. So basically they're similar, and the baseline, for example, for the fossil fuel consumption, the baseline scenario shows a fossil fuel consumption of 30 TJ, while scenarios with a low share of a B for battery electric vehicles, scenarios A and B, show an increase of fossil fuel consumption between 22% and 43%. And the scenario B with a low share of the battery electric vehicles and optimistic assumptions of the PAVs has the highest consumption of fossil fuels, while the scenarios C and D, while it translated a share of battery electric vehicles compatible with the climate neutrality targets, presents the lowest fossil fuel dependency. When comparing the different power generation mixes, it is clear that energy mix 1, pre-Fukushima, has the highest consumption of the fossil fuels for all PAV penetration scenarios, given its high share of the fossil fuels in the power generation mix. Thus, this energy mix is not considered desirable due to the potential risks associated with nuclear energy. And the energy mix 2, the current policies result in a relatively lower consumption of the fossil fuels than the baseline, but energy mix 3, high renewables, no nuclear, has the lowest fossil fuel assumptions. While for the other local air pollutants, here we show you the results for the sulfur oxide, particulate matter, and the nitrogen oxides by 2050. So the alternative scenarios lead to a substantial increase in the local air pollutants compared to the baseline scenario assumptions, especially if the power generation mix follows the baseline pre-Fukushima and the current policy of trains. This rise is mainly due to the introduction of PAVs in all alternative scenarios, which leads to the increase in the travel demand. And for instance, in the scenario A, the PM 2.5 emissions range from 150 to 166 kilograms yearly, which are around 27% higher than the baseline trend. A more optimistic value of the time and consumption in scenario B leads to even higher emissions, and which is around 50% higher than the baseline trend. It is especially interesting to notice that assuming the higher penetration of battery electric vehicles without forcing the expansion of the renewable energies in the power grid would be even more impactful in terms of air pollutants. So scenarios C and D considers a power grid equivalent to the pre-Fukushima power generation portfolio, and following current policies would increase emissions of all local air pollutants. So one of our main conclusion here is that only with the expansion of the battery electric vehicles coupled with decarbonization of the power grid through the expansion of the installed capacity of renewable energies would decline local air pollutant emissions when compared to the baseline trend. So here we show you the discussion and the conclusion for this study. So again, we hear the thing we want to highlight here is that even that Gunma want to promote the use of electric vehicles here, we emphasize that to couple it with the combination of a power grid through the expansion of capacity of renewable energies is very important to achieve such kind of zero greenhouse gas emission. And here we also show you some limitations here for this study. Some notable things like some notable limitations here is like, for example, the historical data on new vehicle sales used in the analysis is at the national level, which does not consider specific conditions in the Gunma Prefecture, so which which could have some room, the potential for underestimation of the total emission effects. And also the travel behavior simulation of the four alternative scenarios suggests the decline of the average speed of PAVs according to the results, so which may result into more efficient powertrains, but that is not reflected in the current methodology we used. And thank you, that's all from me. And here are the reference.
Thank you, Lichen, and also thank you, Giancarlo, for sharing the link to the paper. It's very interesting research. Well, last week, actually, I had a debate in my class about EV tax versus EV rebate. In Australia, we are actually doing really bad in terms of the adoption of battery electric vehicles. The battery electric vehicles, BEVs, the adoption rate is so low, it's almost negligible, basically. If it is just like, I think 8,000 over 2 million of registered cars. But also what we were kind of discussing, and students actually discussing over that debate, was that, well, we have to first look at the total life cost analysis. We have to look at the source of the energy for charging batteries. Every battery electric vehicle doesn't mean that it's necessarily purely green. And also because I think from your simulation, what we learned was that it led actually to higher vehicle kilometer traveled, right? And that also kind of impacted even on the environmental impact.
Yes.
Yeah, so that was actually interesting, and your presentation was very clear. I didn't have any I don't have any particular question. Let's see if there's any question in the room. Yeah, and also it's really interesting to see and to read this paper. So please, everyone, if you're interested in this research, go and click on that link and then study. I'm going to do it just immediately after this. Okay, so thank you, Lichen. Thank you, Giancarlo, and thanks to you for presenting. Very well done. So, okay, let me just go to the next presenter, who is Jiqian Dong. And Frank, Jiqian actually is also known as Frank. Frank is a PhD candidate in the School of Civil Engineering at Purdue University as a graduate research assistant at the Center of Connected and Automated Transportation. Before joining Purdue, he received his master's in civil engineering and bachelor's from Carnegie Mellon University and also Junxia University. So, well, Frank actually emailed me this morning and he said that he will not be able to present himself, but he has recorded himself. And he's actually flying to another conference on connected automated vehicles. So it will be 3 a.m. in his time, unfortunately. But let me share my screen. Well, actually I had it, but I have to share with voice this time. So when I'm going that, then share sound. Yeah, awesome. Let me know if you can hear Frank. Okay, let me just play it.
Hello, everyone. Welcome to the BTR 5 conference, and thank you very much for coming to my presentation. I first need to apologize. I'm not able to present in person because we have an autonomous racing event tomorrow. I will share you with some information later on. Okay, so my name is Jiqian Frank Dong. I'm a fourth-year PhD candidate at Purdue University. Today, my topic is called the Model-Based Reinforcement Learning for Connected Autonomous Vehicle Under Safety Imminent Situation. It's a very long title, but don't worry. I promise it will be super simple. Like the idea is very, very simple. The methodology is simple, and the result, of course, is very easy to understand. Okay, let me start with the background. So the vehicle automation and the future intelligent transportations. So there are a lot of anticipated benefits behind that. First, it will increase the mobility by increase the road capacity, reduce the parking availabilities for sure, and will enhance the efficiency because there will be no congestions anticipated. Increase the safety by eliminating the human error, which is the cause of 94% of the accidents. Enhance the sustainability by producing less emissions and less fuel consumptions. And above all, which is my favorite, you can have more free time during the commuting, which is really good. You can do whatever you want during the time you're in the car, right? So there's an interesting, like the survey done by Intel, and it is said like there will be more than 250 million hours of users commuting time will be saved every single year, and more than 500,000 lives will be saved within from 2035 to 2045, and this is only in US. Like if you think about like it is from a global scale, like the more benefits can be anticipated. Everything of this relies on the automation and the connectivity. Okay, despite with this anticipated benefits, we are still far from there, right? So as the very beginning, like, do you really trust the AVs? And are they actually as safe as they sound? They claim they can achieve the Vision Zero, but how do I know, right? Do you really trust the AVs? So there's a survey done by the NHTSA, which is the US government, which said like the Tesla's autopiloting function actually can reduce 40% of the crash. So 40% of the crash rates by introducing this function. So indeed, like it is helping us, right? The autonomous driving function, it's really good. And still, but like the advocates of the highways and auto safety, they did another survey in 2018, the same year, and saying like 75% of the people, they are not comfortable with disconnecting the vehicle equipment. That means like 75% of people, they do not really want to have an autonomous vehicle. At least the vehicle, they don't have like the steering wheels, the pedals, the brake stuff, and it's completely controlled by the autonomous agent. Like the human are not able to accept that. And also 64% of the people even show that there are severe concerns towards sharing the same road with the AVs. They don't even want to drive on the same road as the autonomous vehicles. But from this, like the report, it's a governmental report, is absolutely true. Like the autonomous driving function is actually safer, but why people are still so conservative? Right. By looking into this thing, and this can lead into the motivation of this project. So why people are conservative? To begin with, the testing of the autonomous vehicle itself is kind of troubleshooting. So we all know there will be a curse of sparsity, especially for the dangerous scenarios. That means the autonomous vehicles can be tested mainly in the constrained, like the restrained locations and with specially designed scenarios, and they can guarantee the safety. That means like no matter how hard you try, you test the autonomous vehicles, they are still in the safe environment. They are not exposed to those ones that are malicious, that are adversarial, that can make them crash, right? So as a result, right, even if they have been tested like for how many hours, they are still, still do not know whether they are safe enough to behave in the dangerous scenarios, because they don't have the money, the time to kind of test in those risky scenarios. And the second thing is that actually the autonomous system itself, majority of the efforts that people kind of pour into is to prevent the AV, the autonomous vehicles, that to make mistakes. So what if when other people makes mistakes? So basically, you're driving a road, someone is drunk maybe, and he's kind of driving aggressively, he can crash into you very easily. So how do AVs kind of respond to the errors that made by others? When surrounding people are at fault, what can we do? So this perspective, we don't have a safety guarantee for the majority of the existing autonomous vehicles, right? And the third thing is that the AI system, majority of the AV systems are driven by the AI system, which is artificial intelligence. Basically, for those things, especially for the perception, the camera processing and stuff, they require a heavy dose of the deep learning, or even sometimes they use reinforcement learning for the decisions. So these AI systems are generally considered as black boxes. And we don't really know how the AI makes the decisions. So the rationale behind that is unknown. And what's even worse is that when the AI will fail is not predictable. We don't really know when it will lose the control and then causing the crash. We have no idea. And we don't generally know how to improve such black box behaviors, right? You have a model and you have no idea how to kind of make it better. So with these three severe problems, and then we kind of understand, okay, with this not solved, people are always conservative. So generally, what we are trying to tackle with these three challenges that in this specific project is that for the testing, the troubleshooting, we're kind of trying to build some challenging testing scenarios for the autonomous vehicles to travel. Also, we still use the simulation test, and we want to improve the fidelity of the simulation test, and then to guarantee the AVs can be running safely. And also, we build a emergency response AV system instead of it's actually a proactive system when others are making mistakes. What can we do, right? So to look into this scenario when others make mistakes. And the third, to tackle the black box behavior, we want to make the AI models more kind of explainable. So that's a reason we are using the methodology to combine machine learning, the data-driven approach, and with traditional control. With this being said, let's look into the problem settings. What kind of situations we want to solve here? So here, as you can see, we are driving the red vehicle, and there are some drunk drivers. For example, this yellow vehicle. He is driving aggressively and then makes a lane change to crash into us. So we want to avoid this kind of situations when others are at fault. There are challenges behind that. Of course, the computation need to be really fast. We are dealing with like a highly dynamic surrounding environment problems. So the number of vehicles surrounding us is always changing. The types of the vehicles are also changing. The type of the corridor shape is also changing. So we want to avoid the collision with the at-fault vehicle, but not at the same time not creating new collisions with other vehicles. So we have the safety requirements. So that's the reason we are trying to solve this by combining the traditional control into the machine learning and to make the entire system more reliable and safe. Okay, so for the general methodologies, so I'll give you a little bit of background of why we are choosing this learning plus control framework. So they are purely learning-based methods. The pros are like they have the very high representation power. They can do like the fixed time inference, and it's very scalable. For example, the neural networks, you just need to fill in the input and then it will generate the output, no matter how complicated your input is. But the cons are also obvious. Of course, the black box behavior, it requires like the massive data for training and general lack of safety guarantee and the convergence guarantee that is very bad. For the traditional optimization-based control or planning approaches, their pros are like they have the very high interpretability. The model itself is completely transparent. You can read every single perspective. And it doesn't require any sample data, which is very data efficient. But the cons are generally they also requires like a given plant model, which is like the state transition model. This is very hard to derive, especially in the highly dynamic and complex situations. And it needs multiple assumptions to guarantee the solvability, because the problems can easily turn into non-convex, and you will have a problem. So by combining these two approaches, like the learning-based and also the traditional optimization-based, we can have the model-based reinforcement learning, and this can yield the maximum benefits. Okay, so what is the model-based reinforcement learning? Or in another word is, you can call it the neural MPC as an example, which is a model we are using here. So it has several components. First, it has a model, which is obvious, if the name suggests, which the model kind of predicts the situation of the system. So for example, here we are predicting like the future trajectories of all the surrounding vehicles, including the at-fault vehicle and also my ego vehicle. And with this model, we can do planning based on that. So here, the planning is a optimization-based method. Right, so combining these two, we have the model predictive control, and by executing the control command, we can kind of consistently acquire new data, and then we have the new experience, right? And then we can use this data to improve our model, so it becomes a loop, and the model is continuously becoming better and better. So for the model, what we are trying to do is that you're giving the historical state of the vehicles, and then you predict the future states. For example, you give the historical trajectories, the XY locations, the speed, acceleration, and you predict the future, where the vehicle will be, and then you use this model to determine, okay, how close my ego vehicle is to that vehicle, and then do this. So we are kind of trying to fine-tune a model on the fly. Basically, this model is keep changing at each time step, so we can only afford like fine-tune those smaller models. For example, the linear regression model, which is very simple, and the LSTM, which is just very basic model, or very shallow neural networks. We cannot say the deep neural networks here because we are only using shallow neural networks to guarantee the safety, to guarantee the computation speed. Sorry. Okay, so the methodology we are using here is called the MPC with the CEM optimization for the planning perspective. So at each time step, you randomly generate N trajectories. So action trajectories, you randomly move your kind of steering wheels and stuff, pedal positions. And you use the learn model, which is the state prediction model, to generate the state trajectories, basically to determine what will be the future location speed for your ego vehicle and the rest of the surrounding vehicles. And then you evaluate all these action trajectories to get a cost function. We have a cost function to evaluate the state. And then you pick the best K trajectories, refit your initial sample trajectory to these K trajectories, and then redo it after several iterations. Basically, you kind of concentrate your kind of the random actions into the better ones, right? You concentrate those to the optimal trajectories. And then you pick the best trajectory after some iterations, and then only execute the first action. So despite it has a lot of steps, the key idea is very simple. You just like two old men playing chess. One man predicts the behavior of the other man, and then plan accordingly. So how can he predict the behavior of the other man? Is like, this is part of the modeling part, right? The model-based reinforcement learning. The model is to estimate the behaviors of others and then to make the planning accordingly. So here is the full algorithm. I will skip this part because the time is too limited. So for the experiment setting, what we have here for the state space and action space, and of course the cost function. So for the state space, we are considering the human-driven vehicles, the HDVs, and also the ego vehicles. We call that the CAVs, the connected autonomous vehicles. So we have the location, speed, and acceleration for each of the vehicle. So, but for the CAV specifically, we also have the control command, right? The gas position, the steer, the brake for the past few time steps, right? We can get that. And with that, we can predict the future state. So what are the actions we need? So here we are only considering the kind of a discretized actions. So we kind of discrete the steering angles to -1, 0, and 1, which is like the left increment by, for example, 5 degrees, keep, or right increase by 5 degrees at each time step. So it's a discrete action. For the throttle and brake, we also kind of combine them into some discrete actions. So -1 is brake, 0 is keep, and +1 is throttle. This is mainly to reduce the sampling space for my cross entropy optimization. So for the cost function, we are trying to use the time to collision for the ego vehicle to the rest of all the surrounding objects, including the dynamic objects and the static objects. So we pick the best action trajectories with this minimum total time to collision. Okay, then I will introduce the dataset we're going to use for developing and testing our model. So we are using the synthetic dataset, which is collected from the color simulator. We are developing this kind of very conservative scenarios in the color. For example, this yellow vehicle, they are very close at the very beginning, and but the yellow vehicle will make a huge right turn right in front of the red vehicle. So we are assuming a very big constant steering angle. And this is only used for developing our model. For the testing, we are using the real, like the driving simulators. We ask our participants to drive as aggressively as you can. So also we create this kind of dangerous situations for them so they can avoid the collision by driving aggressively. Yeah, so we are trying to induce them to drive aggressively. So this can be used to test whether our model is perfectly designed or not. Okay, so for the results, as you may think, okay, I may use two simple like the models. For example, the 3-layered fully connected neural networks or 1-layer bilinear LSTM, long short-term memory model, or the linear regression model. But the results indicate like even the linear regression model can do a pretty good job. So here are the like the arrows, the mean squared errors for the location and the velocity prediction. So these are the two values we needed to compute the TTC. So here you can see from the quantitative like the evaluation, you have the historical trajectory, which is this line, and then you have a dot for the prediction and the star for the ground truth. You can see our model can actually, even like the linear regression model can do a decent job by having a very low level of noise. So you can, for the CAV, it can predict even better because we have the control command, additional information. Okay, we are trying to demonstrate the performance of our model by showing the success rate, which is the collision avoidance success rate, and also the computation time for the model to depends on different like the model parameters. We are having the different like the planning horizon, the number of random trajectories you sampled, the number of cross entropy methods iterations, and that determines like the best performance of the model. As you can see here, those green dots here indicates our model can actually avoid more than 90% of the crash. And you can see here for the quantitative evaluation, the yellow vehicle try to crash into the red vehicle, despite they are very close at the very beginning, but still the red vehicle can kind of act accordingly, like within a very limited time. So that indicates our model is kind of doing it perfectly. Okay, we do some ablation study by varying the initial speed. You may think, okay, maybe in the previous video, it's too slow, the two vehicles, right? We kind of vary the initial speed of all the vehicles in the traffic and to see, okay, still can we avoid the collision? And it indicates that for some of the cases, we can still avoid approximately 90% of the chance, even at the 25 meters per second, which is like more than 100 kilometers per hour. As I mentioned before, we also evaluate our model in the real, like the human drivers, like the trajectories. So we evaluate in the trajectories that we collected in the driving simulator. So we collected a lot of left and right lane changes, and we kind of define the aggressiveness by using the average lateral speed. So how much you travel in the lateral direction, in the given time. So we can see, okay, some of the trajectories are very conservative. For example, this green one. Some of them are very aggressively. For example, the red ones. Right. So the key idea here is that we can still achieve a pretty decent or even higher, like the collision avoidance rate, more than 95%. So that generally indicates that our efforts of like building the model in the conservative simulation scenarios and the testing in the real scenarios, that can actually work. Right. So that gives us the confidence, okay, we can actually test the autonomous vehicles by placing them in the dangerous scenarios, in the more conservative, dangerous situations, so that at the real world, they can still perform good. So for a little bit of conclusion here, we built a very simple algorithm. So basically the model plus the planning, and we achieve the awesome performance. So by awesome, I mean like it has a high kind of successful rate for crash avoidance, even in a very highly dangerous situation. And you can achieve faster computation. This is only run on one GPU, and it even includes the simulator rendering and everything. So the computation is very small. And the cost of the training on the conservative cases, test on the real trajectories, this actually work. And it can guarantee, okay, we still can afford that. And also the learning-based approach in the dangerous situations, it's also a proof of the concept. For the future of the work, we can consider like the multi-agent control. So for example, for the autonomous vehicles, it can not only control itself, but also control the surrounding vehicles to create such kind of gap for him to avoid the collision. And we can test the system with some more dangerous scenarios, for example, some rear ending cases, or even the front ending, very dangerous cases. Yeah, that's the future plan. Okay, this actually concludes my presentation, and I thank you for all your attention. Again, I have to apologize, I cannot present in person because we will have a autonomous racing event tomorrow. So here you can see it's our autonomous racing car. It's a full-sized car, but no man inside. Yeah, it's pretty cool, right? And tomorrow will be the racing day. And I really welcome if you have any questions and comments, or if you want to collaborate with us even on this autonomous racing project. And here are my the contact information. Feel free to connect me at any time. Thank you.
Hey. So thank you so much for listening. That was the last presentation of the Eastern track. So we kind of finished the BTR on the Eastern track, but we're actually looking forward to the headliner speech by Professor Patricia Mokhtarian from Georgia Tech University. She used to be a professor in University of California, Davis, if I'm not wrong. Yeah, she will actually give the headliner speech in 8 hours from now. So if your time zone allows you to stay awake, I encourage you to also tune in for that headline speech. And after that, there will be also more sessions, particularly the TRB special session, I reckon. So you can again check out the conference program on the Western track. So I would like to really thank everyone for your contribution, for submitting your paper to BTR. And before just I wrap up the conference, again, I would like to reiterate that what has been the motivation behind the BTR, which is an online conference. Well, in fact, the motivation was providing a platform for all of the researchers around the world if they cannot afford paying the registration fee for the conferences, or they cannot get visa, or they cannot travel for any family commitment, disability, being pregnant, I don't know, anything, taking care of someone. But still, without that, we should keep it alive. And we started before COVID. So actually this year was the 5th year. We're going to continue. So if you would like to also become an organizing committee member, please just email us. You have, I reckon you have my email because I have contacted all the presenters as well as registrants. You can find my information, or Professor Karakokomer. So please hand up if you really like to volunteer. So what we would do is just editing the videos or recordings, and then we would share it on YouTube on our BTR channel, the YouTube BTR channel. We also provide a hyperlink on our website. So you can also find the archive of all of the presentations and recordings from previous years on our website, as well as the YouTube channel. So that will be it. Thank you. And thanks also to all of the other organizer committee members. I can see Gian Carlos, Gina, I reckon that Shams and others would be in other sessions. So thanks actually to everyone.
Thank you. See you next year.
Thank you.
Yeah, see you next year. Thanks.
Thank you very much. See you soon.